You are listening to Building the Internet of Things, from concept to connected device with Arduino and Raspberry Pi. Like and subscribe to keep up to date on our latest audiobooks. Building the Internet of Things, from concept to connected device with Arduino and Raspberry Pi. Chapter 1, The Dawn of Connected Things, Understanding the IoT Landscape. 1.1 Introduction, where everything connects. Imagine a world where the everyday objects around you could talk. Not in a magical, whispering way, but by sharing valuable information about themselves and their environment. Your refrigerator could tell you when you're low on milk. Your car could warn you about a bumpy road ahead before you even see it. And your house could adjust its temperature automatically based on who's home and what the weather is doing outside. This isn't science fiction. This connected reality is the essence of the Internet of Things, or IoT 1.1.1. What is the Internet of Things, IoT? At its core, the Internet of Things is a network of physical objects embedded with sensors, software, and other technologies for the purpose of connecting and exchanging data with other devices and systems over the Internet. Think of it as allowing inanimate things to perceive, communicate, and act. These aren't just your computers and smartphones anymore. The things in IoT can be incredibly diverse. From wearable fitness trackers and smart home appliances to industrial machinery in a factory, livestock on a farm, or even entire city infrastructures like smart traffic lights or connected waste bins. Each of these things is given a unique identifier and the ability to transfer data over a network without requiring human-to-human or human-to-computer interaction. It's an evolution in how we interact with the physical world, bringing digital intelligence to an astounding array of objects. 1.1.2 A brief history of connectedness. While the term Internet of Things might sound like a modern invention, the concept of ubiquitous computing has roots going back decades. In 1988, Mark Weiser, a computer scientist at Xerox PARC, envisioned ubiquitous computing, where technology would seamlessly blend into our environments, becoming invisible yet constantly present. He spoke of a world filled with sensing devices that could adapt to our needs without direct interaction. One of the earliest, albeit unofficial, IoT devices emerged in the early 1980s at Carnegie Mellon University. Students and professors, tired of trekking to a vending machine only to find it empty or warm, fitted a Coca-Cola machine with sensors connected to their computer network. This allowed them to remotely check the stock levels and ascertain if the sodas were cold before making the journey. It was a simple solution to a common frustration, but it embodied the fundamental principle of IoT, enabling remote monitoring and intelligent decision-making about a physical object. As the Internet grew, so did the potential for connecting devices. Machine-to-machine, or M2M communication, where devices communicated directly with each other, paved the way. Technologies like radio frequency identification, or RFID, which allowed for digital identification of objects, further expanded the possibilities of tracking and managing items. The actual term Internet of Things was coined in 1999 by Kevin Ashton during a presentation at Procter & Gamble. He primarily used it in the context of supply chain management, envisioning a future where every object could explain itself and its journey, reducing waste and improving efficiency. From these diverse origins, fueled by advances in wireless technology, miniaturization, and computing power, the Internet of Things slowly but surely began to take shape, moving from academic concepts and niche industrial applications to become the pervasive phenomenon we know today. 1.2 Why IoT Matters. Impact and transformation across fields. The Internet of Things isn't just a technological curiosity. It's a transformative force reshaping industries, improving daily life, and driving economic growth. Its impact stems from its ability to collect data at an unprecedented scale, offering insights that were previously unattainable. 1.2.1 Enhancing Daily Life. Smart homes and personal devices. Perhaps the most visible face of IoT for many people is in their own homes. Smart home devices promise greater convenience, comfort, and sometimes even safety. Imagine being able to adjust your home's lighting, thermostat, or door locks from anywhere in the world using your smartphone. Beyond mere control, IoT devices in the home often learn from your behavior. A prime example is the smart thermostat. Devices like the Nest thermostat, introduced over a decade ago, revolutionized how people thought about home heating and cooling. Instead of just letting you set a schedule, it began to learn your preferred temperatures, automatically adjust when you left or returned home, and even factor in outside weather conditions. What started as a simple convenience evolved into a powerful tool for energy conservation, showcasing how data collected from environmental sensors and user habits could lead to significant savings and a more comfortable living space, often without conscious effort from the homeowner. Similarly, smart security cameras, smoke detectors, and fall detection systems for elderly care demonstrate how IoT can contribute significantly to personal safety and peace of mind. 1.2.2 Revolutionizing Industries. Industrial IoT, and smart cities. Beyond the smart home, IoT is profoundly transforming various industries, often referred to as the Industrial Internet of Things, or IIoT, and propelling the development of smart cities. In manufacturing, sensors placed on machinery can monitor vibrations, temperature, and other operational parameters. This data enables predictive maintenance, allowing factories to anticipate equipment failure before it happens, scheduling repairs precisely when needed. This prevents costly unplanned downtime, extends the lifespan of machinery, and improves workplace safety. Consider a scenario where a critical pump in a chemical plant begins to show subtle signs of wear through increased vibration, detected by an IoT sensor. The system alerts maintenance crews, who replace a worn component during a scheduled break, averting an expensive and dangerous breakdown that could have halted production for days. This foresight, driven by data, marks a huge leap in efficiency. In agriculture, IoT sensors are used to monitor soil moisture, nutrient levels, and crop health across vast fields, enabling precision farming. Farmers can optimize irrigation and fertilization, conserving resources and increasing yields. Smart waste management systems use sensors in bins to signal when they are full, optimizing collection routes and reducing fuel consumption and emissions in cities. Public services are being streamlined through smart streetlights that adjust brightness based on ambient light or traffic, and traffic management systems that dynamically alter signal timings to alleviate congestion. 1.2.3 Data-driven decisions. The power of information. The true power of IoT lies in its ability to collect vast amounts of data and transform it into actionable insights. Every sensor reading, every device interaction contributes to a growing pool of information. This raw data, when processed and analyzed, reveals patterns, trends, and anomalies that can inform better decisions, optimize processes, and even create entirely new business models. From understanding consumer behavior in retail to optimizing energy usage in commercial buildings, IoT data provides a foundation for unprecedented levels of intelligence and efficiency. 1.3 The core architecture of an IoT system. A high-level tour. While the applications of IoT are diverse, the underlying architecture of most IoT systems follows a common pattern. Understanding these fundamental layers is key to designing your own connected devices. 1.3.1 The things, devices, and edge computing. At the very bottom of the architecture are the things, themselves the physical devices. These are often equipped with two primary types of interaction components. Sensors. These are the eyes and ears of your IoT device. They gather input from the real world, detecting and measuring physical quantities like temperature, light intensity, proximity, motion, humidity, or pressure. Actuators. These are the hands and feet of your IoT device. They take action in the real world based on decisions made by the system. Examples include turning lights on or off, opening valves, starting motors, or displaying information on a screen. Each thing also contains some form of embedded computing, a small, specialized computer that acts as its brain. This brain could be a simple microcontroller, like those found in many Arduino boards, powerful enough to read sensor data and control actuators directly. Or it could be a more complex microprocessor, like those on a Raspberry Pi, capable of running an operating system and performing more sophisticated local data processing, sometimes referred to as edge computing. This local processing reduces the amount of data that needs to be sent to the cloud, improving response times and efficiency. 1.3.2 Connectivity, bridging the physical and digital. Once a device gathers data or needs to receive a command, it needs to communicate. This is where the connectivity layer comes in, bridging the gap between the physical device and the wider digital network. Often, devices connect to a gateway. This is a local hub that translates data from diverse devices into a common language suitable for internet transmission. Think of a smart home hub that connects your smart light bulbs, door locks, and thermostats to your home Wi-Fi network. Communication protocols are the languages devices use to talk to each other and to the network. These vary widely based on range, power consumption, and data transfer rates. Common examples include Wi-Fi for local high-bandwidth connections, Bluetooth for short-range personal device connections, and specialized long-range, low-power options like LoRaWAN for devices many miles from a gateway. The actual data transfer happens over various networks. This might be a local wireless network, a wired Ethernet connection, or even cellular networks for devices in remote locations. 1.3.3 The Cloud Data Center, the central hub. For many IoT systems, data eventually makes its way to the cloud or a centralized data center. This is where the heavy lifting happens. Data ingestion. Cloud platforms are designed to receive vast amounts of data from thousands, even millions, of devices simultaneously, handling the sheer volume and velocity without breaking a sweat. Data storage and processing. Once ingested, data is stored in specialized databases optimized for time series data collected over time. Powerful servers process this data, performing calculations, filtering out noise, and organizing it for analysis. Analytics and machine learning. This is where the magic happens. Sophisticated algorithms and machine learning models analyze the processed data to identify patterns, predict future events like predictive maintenance, detect anomalies, and derive actionable insights. Application Programming Interfaces, APIs. These are standardized ways for other software applications to interact with the IoT data and services in the cloud. This allows developers to build mobile apps, web dashboards, or integrate IoT data into enterprise systems. 1.3.4 User Interface, interacting with your IoT system. Finally, for humans to interact with and benefit from the IoT system, there needs to be a user interface. Without this layer, the collected data and automated actions would remain invisible and uncontrollable. Mobile apps. These are probably the most common interfaces, allowing users to monitor their devices, view dashboards, control settings, and receive alerts directly on their smartphones. Web portals. Browser-based dashboards provide a comprehensive overview and control for more complex systems, often used in industrial or smart city applications. Voice assistants. Increasingly, platforms like Amazon Alexa or Google Assistant provide intuitive, hands-free ways to control smart devices and query their status using natural language commands. 1.4 A glimpse into the future. What's next for IoT? The Internet of Things is not a static concept. It's continuously evolving. We can expect an increasing pervasiveness of connected devices in nearly every aspect of our lives, from smart clothing to intelligent infrastructure. The integration of artificial intelligence and machine learning will move beyond just cloud analytics. AI will increasingly be embedded directly into endpoint devices through edge computing, allowing devices to make more intelligent decisions directly, without constant recourse to the cloud. New network technologies like 5G will provide the high bandwidth and low latency necessary for truly real-time, mission-critical IoT applications. However, this growth also brings critical considerations to the forefront. The importance of robust security and privacy measures cannot be overstated. As more of our lives become connected, ensuring the integrity of our data and protecting our devices from malicious attacks becomes paramount. Ethical considerations surrounding data usage, surveillance, and bias in intelligent systems will also play an increasingly significant role in shaping the future of IoT. This journey into building connected devices requires not just technical skill, but also a thoughtful approach to the broader implications of our innovations. Conclusion and chapter summary. In this introductory chapter, we've laid the groundwork for understanding the Internet of Things. We defined IoT as a network of physical objects embedded with technology to connect and exchange data, moving beyond traditional computing devices into the realm of the everyday. We explored its brief but significant history, from early concepts of ubiquitous computing and the first connected soda machine to Kevin Ashton coining the term. We then delved into why IoT matters, examining its transformative impact on daily life through smart homes and personal devices, and its revolutionary effects on industries and cities through applications like predictive maintenance and smart traffic management, all driven by the power of data. Finally, we looked at the core architectural layers of an IoT system, from the things themselves with their sensors and actuators, through connectivity, the cloud for data processing and analysis, right up to the user interfaces that make these systems accessible. As we move forward, we'll dive deeper into the practical aspects of building these connected things, starting with the brains behind the operation, the versatile Arduino and Raspberry Pi. Further reading, asterisk for a deeper dive into the historical context of ubiquitous computing, search for Mark Weiser's foundational papers. To learn more about the origins of the Internet of Things term, explore Kevin Ashton's original publications or interviews. Look for general overviews of IoT architecture from reputable technology research firms or academic institutions. Chapter 2. The Brains of the Operation, Arduino versus Raspberry Pi. Every Internet of Things device needs a brain, a central unit that processes information, makes decisions, and controls actions. For hobbyists, makers, and even professionals prototyping new ideas, two platforms dominate the landscape: Arduino and Raspberry Pi. While both are immensely popular and capable, they serve different primary purposes, much like specialized tools in a toolbox. Understanding their fundamental differences is crucial for choosing the right brain for your IoT project. 2.1 Microcontrollers versus microprocessors. The fundamental divide. Before we dive into the specifics of Arduino and Raspberry Pi, it's essential to understand the core distinction between the two types of electronic brains they represent: microcontrollers and microprocessors. 2.1.1 Microcontrollers, MCUs, the dedicated specialists. Imagine a Swiss Army knife designed for a very specific task, like opening cans. A microcontroller, often abbreviated as MCU, is a tiny computer that resides on a single chip. Unlike the central processing unit, or CPU, in your desktop computer, a microcontroller is designed to be a complete, self-contained system. This means it typically integrates the central processing unit, a small amount of memory for both programs and data, and various input-output components, all onto that single silicon die. Microcontrollers are like dedicated specialists. They are designed for specific, repetitive, and often time-sensitive tasks. Their strengths lie in their efficiency, low power consumption, and predictable real-time operation. This means when a microcontroller is programmed to do something, it typically does it immediately and consistently every time, making them excellent for tasks requiring precise timing, such as precisely controlling the speed of a motor or responding instantly to a sensor reading. They are generally more cost-effective for simple control applications. Their typical use cases include running washing machines, controlling a child's toy, managing engine functions in a car, or reading values from a simple temperature sensor and turning a fan on or off. They are excellent for automating a single, clearly defined function. 2.1.2 Microprocessors, MPUs, the versatile generals. Continuing our analogy, if a microcontroller is a specialized Swiss Army knife, a microprocessor, or MPU, is more like a full toolkit. A microprocessor is primarily just the CPU, the central processing unit, the thinking part of a computer. To truly function as a computer, it requires external components such as dedicated memory chips, like RAM, storage, like an SD card or hard drive, and separate chips to manage input and output signals. Microprocessors are versatile generals. They are powerful, capable of running complex operating systems like Linux, and can handle a wide range of tasks concurrently. This makes them ideal for applications that require significant processing power, multitasking, complex network communication, or graphical user interfaces. Because they run an operating system, they can support higher-level programming languages and complex software applications, process large amounts of data, and manage multiple complex peripherals simultaneously. However, this versatility comes with trade-offs. Microprocessors generally consume more power, are more complex to set up due to the need for external components, and because they run an operating system, their timing can be less predictable than a microcontroller. They are typically found in personal computers, smartphones, sophisticated industrial control systems, or devices that need to run multiple programs at once, like a web server or a local data analytics machine. 2.2 Meet Arduino. Simplicity for real-time control. Arduino represents the microcontroller side of our IoT brains. It is an open-source electronics platform based on easy-to-use hardware and software, designed to make electronics accessible to artists, designers, hobbyists, and anyone interested in creating interactive objects without needing deep engineering knowledge. 2.2.1 What is Arduino? An Arduino board consists of a specific microcontroller chip, often from the T-Mega family, alongside components that make it easy to power it, connect it to your computer via USB for programming, and interface with sensors and actuators using standardized pin headers. These headers allow you to simply plug in wires or other components. While the classic Arduino Uno is a popular choice for learning, other boards are particularly relevant for IoT. For instance, the Arduino Nano is a compact version, great for projects where space is limited. More significantly, many development boards built around microcontrollers like the ESP32 and ESP8266 have become incredibly popular for IoT. These chips are unique because they have built-in Wi-Fi and often Bluetooth, making them capable network-connected IoT devices straight out of the box. Even though they are programmed using the familiar Arduino Integrated Development Environment, or IDE. 2.2.2 Arduino's strengths in IoT. Real-time performance. Arduino is excellent for tasks that demand precise timing and immediate responses. If you need to read a sensor exactly every millisecond or control a motor with high accuracy, a microcontroller like Arduino excels. Low power consumption. Many Arduino boards and the microcontrollers they use are designed to operate with minimal power, making them ideal for battery-powered or portable IoT devices that need to run for extended periods without recharging. Simplicity and community. The Arduino platform is renowned for its ease of use. It has a simplified programming language based on C++, a user-friendly IDE, and a massive, supportive global community. This means a wealth of tutorials, examples, and libraries, pre-written code for controlling specific components, are readily available. Cost-effective. Entry-level Arduino boards are very affordable, making them a great starting point for experimentation. 2.2.3 Arduino's limitations in IoT. Limited processing power and memory. Arduinos are not designed for complex computations, running graphical user interfaces, or handling large datasets. They have very little RAM and storage compared to a full computer. Lack of operating system. Without an operating system, tasks like managing complex network connections, handling multiple concurrent operations, or interacting with file systems become significantly more challenging and often require specialized libraries. Connectivity often external. While ESP boards solve this, many traditional Arduino boards like the Uno require additional shields or modules to add network connectivity like Wi-Fi, Ethernet, or Bluetooth. Case study example. Consider a simple smart irrigation system. Its main job is to periodically check the soil moisture level using a sensor, and if the soil is too dry, activate a small pump to water the plants until the desired moisture level is reached. This task involves reading a sensor, making a simple decision based on that reading, and controlling an actuator. It's a repetitive, real-time operation that doesn't require complex data processing or an operating system. An Arduino, with its low power consumption and precise control capabilities, is perfectly suited for such a dedicated, efficient, and direct automation task. 2.3 Meet Raspberry Pi. Power and versatility for complex applications. The Raspberry Pi falls firmly into the category of a microprocessor-based system. It's not just a microcontroller board. It's a series of small, surprisingly powerful single-board computers, or SBCS, developed in the UK initially to promote computer science education. 2.3.1 What is Raspberry Pi? A Raspberry Pi board isn't just a chip. It's a complete miniature computer. It features a processor, dedicated RAM chips, various USB ports for connecting peripherals like keyboards and mice, an HDMI output for a display, an Ethernet port for wired networking, and often built-in Wi-Fi and Bluetooth. Crucially, it also includes a set of general-purpose input-output, or GPIO, pins that allow it to interface with electronic components, making it popular for physical computing projects. Similar to an Arduino, the Raspberry Pi runs a full operating system, typically a version of Linux called Raspberry Pi OS, formerly Raspbian. This means you can boot it up, connect a monitor, keyboard, and mouse, and use it much like a desktop computer for browsing the web, typing documents, or even running office software. Popular choices for IoT projects include the powerful Raspberry Pi 4, which is highly versatile, and the very compact Raspberry Pi Zero W, which is smaller, uses less power, and is often dedicated to specific IoT roles. 2.3.2 Raspberry Pi's strengths in IoT. High processing power. Compared to microcontrollers, Raspberry Pis boast significant processing capabilities. This allows them to run complex applications, perform local data analytics, host web servers, handle image and video processing, and even run lightweight machine learning models directly on the device. Edge AI. Operating system support. Running a full operating system simplifies many aspects of IoT development. Networking setup is straightforward, file system management is robust, and it natively supports higher-level programming languages like Python, making complex data manipulation and cloud integration much easier. Rich connectivity. Most Raspberry Pi models come with built-in Wi-Fi, Bluetooth, and Ethernet, making network communication seamless. The multiple USB ports allow for easy connection to various peripherals, from webcams to external storage. Versatile. A Raspberry Pi can act as a central hub for multiple IoT devices, a data logger for sensor data, a local server for home automation, or even a sophisticated gateway for an entire network of simpler IoT sensors. 2.3.3 Raspberry Pi's limitations in IoT. Higher power consumption. Due to their greater processing power and the necessity of running an operating system, Raspberry Pis generally consume more power than microcontrollers. This means they typically require a consistent power supply, e.g., from a wall adapter, and are less suitable for very low-power, long-term battery-operated devices unless substantial battery packs are used. Not truly real-time. Because of the operating system, which manages many background processes, the timing of operations on a Raspberry Pi can be less predictable than on a microcontroller. This makes it less suitable for applications requiring extremely precise or microsecond-level timing. Higher cost. While still affordable, Raspberry Pi boards are generally more expensive than basic Arduino boards, especially when you factor in necessary accessories like a power supply, SD card, and case. Larger physical footprint. Although remarkably small for a computer, a Raspberry Pi board is generally larger than most Arduino boards, which can be a consideration for very compact IoT devices. Case study example. Imagine building an advanced home automation hub. This device needs to collect data from various simple sensors, like temperature and motion, but also host a local web interface for users to control lights and appliances, manage a database of past sensor readings, and communicate with a cloud service to send aggregated data for long-term storage and advanced analytics. The Raspberry Pi's processing power and its ability to run a full operating system make it the perfect choice for such a complex hub, as it can handle multiple tasks concurrently and interact with web technologies. 2.4 Choosing your brain. Picking the right platform for your project. The decision between Arduino and Raspberry Pi boils down to the specific needs of your IoT project. There's no better overall. There's only better for this particular job. Here are the key decision factors to consider. Complexity of task. Is your project about simple control, e.g., turning an LED on-off, reading a single sensor, or complex data processing, running multiple applications, or needing a graphical user interface? For simplicity, think Arduino. For complexity, think Raspberry Pi. Power requirements. Will your device be battery-powered and need to run for weeks or months, or will it have a constant power source? Long-term, low-power operation leans towards Arduino. Real-time needs. Is precise and highly consistent timing critical for your application, e.g., specific motor control, immediate sensor reaction? If so, Arduino is often the stronger choice. Connectivity needs. Do you just need basic sensor input, or do you require robust network capabilities, like hosting a web server or connecting to multiple cloud services? Raspberry Pi excels here, though modern Arduino-compatible Wi-Fi modules are very capable for simple cloud communication. Budget. While both are accessible, basic Arduino boards are typically more economical for starter projects. Programming language familiarity. Arduino primarily uses a simplified C++ style, which is often a first step for beginners in physical computing. Raspberry Pi, running Linux, is very popular with Python, offering a high-level scripting environment for web and data-intensive tasks. Choose what you are more comfortable learning or working with. The analogy. If your project needs a simple, reliable switch that can respond quickly and efficiently to specific inputs, then Arduino is your go-to. If your project demands a miniature computer capable of making complex decisions, running multiple programs, and talking to the internet with ease, then Raspberry Pi is the clear winner. It's also important to note that these platforms are not mutually exclusive. Many sophisticated IoT solutions employ hybrid approaches. For instance, you might use several Arduino boards, optimized for low power and precise real-time control, to gather sensor data from various locations. These individual Arduinos might then communicate with a central Raspberry Pi, which acts as a powerful gateway, consolidating the data, potentially performing local analytics, and then sending the processed information to the cloud. This leverages the strengths of both platforms, creating a robust and efficient system. Conclusion and chapter summary. In this chapter, we've explored the fundamental architectural differences that define the two most popular brain choices for your IoT devices: microcontrollers and microprocessors. We introduced Arduino as a prime example of a microcontroller-based platform, highlighting its strengths in real-time control, low power consumption, and ease of use for dedicated, simple tasks. Conversely, we examined the Raspberry Pi as a versatile single-board computer, capable of running full operating systems, handling complex computations, and offering rich connectivity, making it suitable for more demanding applications. The choice between Arduino and Raspberry Pi isn't about superiority, but about suitability. It depends entirely on the specific requirements of your project, its complexity, power constraints, real-time demands, and connectivity needs. Often, combining their strengths in a hybrid system can provide the best of both worlds. Armed with this understanding, you are now better prepared to select the right central processing unit for your future connected creations. Next, we will delve into how these remarkable devices begin to perceive the world around them by exploring the fascinating realm of sensors. Further reading, **. For a comprehensive understanding of specific board models and their detailed technical specifications, visit the official websites, ArduinoCC and RaspberryPi.org. Many online tutorials and community forums also offer comparisons and project examples that highlight the unique capabilities of each platform. Chapter 3: Sensing the World. Input from the environment. Think about how humans interact with the world. We see, hear, touch, taste, and smell. These senses allow us to gather information from our environment and respond accordingly. In the same way, for an Internet of Things device to be truly smart and reactive, it needs its own set of senses. These are provided by sensors, electronic components that act as the device's eyes, ears, and even nose. 3.1 Introduction. the eyes and ears of your IoT device. Sensors are devices that detect and measure physical quantities or events, and then convert them into electrical signals. These signals can then be understood and processed by the brain of your IoT device, whether that's an Arduino microcontroller or a Raspberry Pi microprocessor. Without sensors, an IoT device would be like a robot performing a fixed routine, unaware of any changes in its surroundings. It might dutifully turn on a light at 7 o'clock p.m. every day, regardless of whether it's still bright outside or if no one is even home. With sensors, the device becomes intelligent and reactive. A light sensor could tell the device that it's already bright enough, while a motion sensor could alert it that no one is present, allowing the device to make a more informed decision, like keeping the light off to save energy. Sensors provide the vital input that allows an IoT system to perceive its environment. This information then enables the device to make decisions, trigger actions via actuators, which we'll discuss in the next chapter, send data to the cloud, or alert a user. A fundamental concept when discussing sensors is how they convey information. Analog signals are continuous and variable, much like a dimmer switch that can be set to any brightness level between off and full on. Many natural phenomena, temperature, light intensity, pressure, are analog in nature. Digital signals are discrete, typically representing just two states, on-off, high-low, or 0-1. Think of a simple light switch. Many modern sensors convert their readings into a digital format internally before sending them to your Arduino or Raspberry Pi 3.2 common sensor types for IoT projects. The world of sensors is vast, but many common types are highly applicable and accessible for IoT projects. We'll explore some of the most frequently used ones, understanding their basic operation and common applications. 3.2.1 temperature and humidity sensors, e.g., DHT11, DHT22, BME280, DS18B20. These sensors are among the most fundamental for environmental monitoring. How they work. Temperature sensors often rely on components like thermistors, whose electrical resistance changes predictably with temperature. Humidity sensors typically use capacitive or resistive elements that respond to changes in moisture content in the air. More advanced environmental sensors like the BME280 combine temperature, humidity, and barometric pressure sensing into a single unit. These sensors often communicate digitally with your device using a single data pin or a serial interface called I2C, which we will discuss later. Applications. They are crucial for smart thermostats, weather stations, sophisticated climate control systems in smart buildings, controlling ventilation in greenhouses, and even monitoring conditions in industrial settings or server rooms to prevent overheating. 3.2.2 light sensors, e.g., photoresistors/LDR, BH1750, TSL2561. These sensors allow your device to see light and measure its intensity. How they work. A basic photoresistor, also known as a light-dependent resistor, LDR, changes its electrical resistance based on the intensity of light falling on it. More light means lower resistance, and less light means higher resistance. These are simple analog sensors. More sophisticated digital light sensors, like the BH1750 or TSL2561, can measure light intensity in units called lux and communicate via I2C, providing more precise and calibrated readings. Applications. Automatic lighting control systems that turn lights on or off based on ambient brightness, smart window blinds that adjust to sunlight, ensuring optimal plant growth conditions, or for detecting dawn and dusk in a security lighting setup. A photoresistor typically uses an analog input pin on your Arduino, while digital light sensors use the I2C communication pins. 3.2.3 motion and presence sensors, e.g., peer, ultrasonic, IR proximity. These sensors are all about detecting movement or the presence of objects. Peer passive infrared sensor, how it works. A peer sensor detects changes in infrared, IR, radiation, which is emitted by all objects as heat. It doesn't emit anything itself, it passively senses. When a warm body, like a human or an animal, moves across its field of view, it causes a fluctuating change in the IR energy detected by the sensor, triggering an output. Applications: motion detection for security systems, automatically turning on lights when someone enters a room, or for energy-saving solutions in unoccupied spaces. The peer sensor typically outputs a simple high-low digital signal when motion is detected. Ultrasonic distance sensor, e.g. HCSR04, how it works. This sensor works on the principle of echolocation, similar to how bats navigate. It emits a high-frequency sound wave, ultrasonic, and then measures the time it takes for that sound wave to bounce off an object and return to the sensor. Knowing the speed of sound, the device can then calculate the distance to the object. Applications: smart parking assist systems in cars, measuring liquid levels in tanks or silos, proximity detection, e.g., ensuring a robotic vacuum doesn't bump into furniture, or used in robots for obstacle avoidance. This sensor uses two digital pins, one to send the sound pulse trigger and one to receive the echo. The time difference between sending and receiving determines the distance. Infrared (IR) proximity sensor, how it works. This type of sensor typically combines an infrared LED emitter and an IR phototransistor receiver. The LED sends out a beam of IR light. If an object is nearby, the light reflects off it and is detected by the phototransistor, indicating the presence of an object. Applications: used in automated hand dryers, simple line-following robots, detecting a dark line on a light surface, or for detecting if a paper towel roll is empty. Their output can be either analog, varying voltage based on distance, or digital, simple on-off when an object is detected within a certain range. 3.2.4 Environmental gas sensors, e.g., MQ series, air quality sensors. These sensors are crucial for monitoring air quality, gas leaks, and general environmental safety. MQ gas sensors, e.g., MQ2 for smoke gas, MQ7 for carbon monoxide. How they work. These sensors contain a sensing element whose electrical resistance changes when exposed to certain gases. The specific MQ series sensor detects different gases. For example, the MQ2 is sensitive to smoke and flammable gases like methane or propane, while the MQ7 is designed for carbon monoxide. Applications: gas leak detection systems in homes or industrial settings, portable breathalyzers, fire alarms, and general indoor air quality monitoring for ventilation systems. They primarily provide an analog output, meaning the voltage signal changes with the concentration of the gas, allowing you to gauge levels. 3.2.5 Specialized sensors, brief overview. Beyond these common types, a vast array of specialized sensors exists, each serving unique purposes. Soil moisture sensors, crucial for smart agriculture and gardening, indicating how much water plants need. GPS modules provide precise location data, invaluable for asset tracking, navigation, and location-aware IoT applications. Accelerometers, gyroscopes, detect motion, orientation, and rotation, used in wearables, fitness trackers, drones, and gaming controllers. They can tell if a device is tilted, moving, or vibrating. 3.3 Interfacing sensors with Arduino and Raspberry Pi. The principles. While each sensor has its unique way of measuring and communicating, the principles of connecting them to your Arduino or Raspberry Pi share common ground. 3.3.1 General Purpose Input-Output GPIO pins. Both Arduino and Raspberry Pi boards feature a set of pins labeled GPIO, which stands for General Purpose Input-Output. These pins are the pathways for your device to communicate with the outside world. Digital input. Many sensors, like the peer motion sensor, directly output a digital signal, either a high voltage, representing on or 1, or a low voltage, representing off or 0. Your Arduino or Raspberry Pi simply reads whether the pin is currently high or low. Analog input. For analog sensors, like a basic photoresistor, your Arduino and some Raspberry Pi analog-to-digital converters, or ADCS, uses special analog input pins. These pins can measure a varying voltage level that represents the sensor's reading. For example, a higher voltage might mean more light, while a lower voltage means less light. Raspberry Pi itself doesn't have native analog input pins, so you'd use a small external component called an analog-to-digital converter, or ADC, which translates analog voltages into digital numbers the Pi can understand. This process is handled by a separate chip that interfaces with the Pi's GPIO. 3.3.2 Serial Communication Protocols, explaining the purpose conceptually. For more complex digital sensors, which send and receive more intricate data than a simple on-off, your devices use specific communication, languages, or protocols. I2C Interintegrated Circuit. This is a popular and efficient protocol because it uses only 2 wires, plus power and ground, to communicate with multiple sensors or other integrated circuits. One wire is for data, and the other is for synchronizing the timing, the clock signal. Each device on the I2C bus has a unique address, allowing your Arduino or Raspberry Pi to talk to a specific sensor individually, asking it for its latest reading or sending it a command. Digital temperature sensors like the BME280 often use I2C SPI, Serial Peripheral Interface. This protocol is generally faster than I2C and suitable for situations where speed is critical, such as communicating with display screens or SD card modules. It typically uses more wires, at least 4. Data in, data out, clock, and chip select, and is primarily for communicating with a single device or a chain of devices at a time. UART, Universal Asynchronous Receiver Transmitter. This is a very common and simple serial communication method, often referred to as serial communication. It typically uses just 2 wires, one for transmitting data and one for receiving data, allowing 2 devices to talk directly to each other. It's often used for communicating with modules like GPS receivers or Bluetooth modules. Regardless of the protocol, the core idea is that your microcontroller or microprocessor asks a sensor for its data using a specific sequence of electrical pulses, and the sensor responds by sending back its reading in a format that the device can interpret. 3.3.3 Conceptual Programming for Sensor Reading. When you program your Arduino or Raspberry Pi to read a sensor, you're essentially providing instructions on how to communicate with it and interpret its data. For instance, for a digital sensor like a peer, your code might simply say, check the state of pin 2. If it's high, motion is detected. For more complex digital sensors, you would tell your device to establish communication using a specific protocol, like I2C, then send a command to the sensor to request a reading. The sensor would respond with raw data, often a sequence of numbers, and your program would then convert those numbers into meaningful values like degrees Celsius for temperature or lux for light intensity. This process is greatly simplified by libraries. A library is like a pre-written set of instructions that handles all the intricate details of communication for a specific sensor. Instead of you having to manually manage the precise timing of electrical pulses or interpret raw data bits, you can simply include the sensors library in your program and then use simple commands like get temperature or get distance. This abstraction allows you to focus on the overall logic of your project rather than the low-level communication specifics. Case study. Imagine building a simple animal presence monitor for your garden. You want to know if animals are visiting, but only at night to avoid false alarms from human daytime activity. You would use a peer sensor to detect motion and a light sensor, like an LDR, to determine if it's dark enough. Your Arduino or Raspberry Pi program would conceptually work like this. First, it would read the light sensor's value. If the light sensor indicates it's dark, e.g., the light value is below a certain threshold, then and only then would the device start checking the peer sensor for motion. If the peer sensor then detects motion while it's dark, the device could send an alert to your phone or trigger an action like turning on a camera. This example shows how combining readings from multiple sensors can lead to more intelligent and context-aware behavior from your IoT device. 3.4 Tips for sensor selection and usage. Choosing and using sensors effectively requires some practical considerations. Accuracy versus precision. Accuracy refers to how close a measurement is to the true value. Precision refers to how close repeated measurements are to each other, even if they're all consistently off from the true value. For many hobby projects, high accuracy might not be critical, but understanding the difference helps you choose the right sensor for your needs. Do you need to know the temperature to within 0.1 degrees Celsius, or is hot, cold, or just right good enough? Environmental factors. Always consider the environment where your sensor will operate. Will it be exposed to extreme temperatures, moisture, dust, vibration, or direct sunlight? Sensors often have operating temperature ranges, and some require protection, e.g., waterproof enclosures. Power consumption. Sensors vary widely in how much power they consume. If your IoT device is battery-powered, you'll want to select low-power sensors and strategically put them to sleep when not needed to extend battery life. Calibration. Some sensors, particularly analog ones or those used in highly precise applications, might require calibration. This involves adjusting their readings to match known standards or environmental conditions to ensure they provide accurate data. Safety precautions. When working with certain types of sensors, especially those dealing with high voltage, hazardous gases, or in industrial settings, always prioritize safety. Ensure proper handling, circuit design, and use of safety equipment. Conclusion and chapter summary. In summary, sensors are the indispensable inputs for any IoT device, enabling it to collect data and perceive the real world. We've explored common types like temperature, light, motion, and gas sensors, understanding their basic operational principles and diverse applications. Crucially, we discussed how these sensors interface with your Arduino or Raspberry Pi through GPIO pins for simple digital or analog readings, or via more complex serial communication protocols like I2C, SBI, and UART for digital data exchange. We also highlighted the conceptual role of programming and libraries in making these interactions manageable, showing how combining sensor data leads to smarter outcomes. With a firm grasp of sensing the world, our next step is to explore how your IoT devices can, in turn, act upon the data they gather. This leads us to the realm of actuators, the components that allow your device to make things happen in the physical world. Further reading. Many hardware suppliers like SparkFun and Adafruit have excellent tutorials and detailed product pages for individual sensors. These resources often include conceptual explanations, wiring diagrams, and example code snippets. Searching for how a sensor works on reputable electronics education sites can also provide deeper insights. Chapter 4. Acting on Data, Making Things Happen with Actuators. In the previous chapter, we explored how IoT devices gain their senses, allowing them to perceive the world around them through sensors. But sensing alone doesn't complete the picture of a truly interactive and impactful IoT system. What good is knowing the room temperature if you can't automatically adjust it, or detecting motion if you can't respond with a warning? This is where actuators come into play. 4.1 Introduction: Giving your IoT device the ability to act. If sensors are the eyes and ears of your IoT device, then actuators are its hands, feet, and voice. An actuator is a component that translates an electrical signal from your Arduino or Raspberry Pi into a physical action or observable change in the environment. They are the components that allow your IoT device to interact with the physical world, moving parts, creating sounds, displaying information, or manipulating environmental conditions. The beauty of combining sensors with actuators is that it creates a feedback loop. A device senses a condition, analyzes the data, makes a decision, and then acts upon that decision. This closes the loop between the digital world of data and the physical world of action, creating truly intelligent and responsive systems. 4.2 Common actuator types for IoT projects. Just like sensors, there's an entire ecosystem of actuators designed for various purposes. Here are some of the most common and versatile types you'll encounter in IoT projects. 4.2.1 Visual feedback, LEDs and displays. Often, the simplest way an IoT device can communicate is through light. LEDs, light-emitting diodes. These are perhaps the most basic and fundamental actuators. An LED converts electrical energy into light. They can be used as simple indicators, e.g., device on, sensor triggered, data uploaded successfully, or as part of more complex visual outputs like status arrays or decorative lighting. They are digital, they are either on or off. However, by rapidly turning an LED on and off, something called pulse width modulation, or PWM, which we'll discuss shortly, you can make it appear to glow at varying brightness levels. Displays LCD and OLED. For more detailed information, small digital displays are invaluable. LCDs, liquid crystal displays, often monochrome like calculators. These are great for showing text messages, sensor readings, e.g., current temperature and humidity, or simple status indicators. They often use I2C or other serial communication for connectivity. OLEDs, organic light-emitting diodes. These are typically smaller, brighter, have higher contrast, and often allow for graphics in addition to text. They also consume less power when displaying dark content. They are excellent for compact, interactive applications. Applications: status indicators on a smart thermostat, displaying a friendly message on a smart pet feeder when it dispenses food, showing room temperature on a display, or alerting users with a blinking light if a security breach is detected. 4.2.2 Audible feedback, buzzers and speakers. Sometimes, a sound is the most effective way for an IoT device to get your attention or provide feedback. Buzzers, piezo buzzers. These tiny components produce a simple beep or buzz when an electrical current is applied. They are ideal for straightforward audible alerts. A basic buzzer produces a single tone, but you can also find programmable buzzers that can play simple melodies or varying tones. Speakers with audio modules. For more complex audio outputs, like voice alerts, sound effects, or playing music, you'd integrate a small speaker with an audio module, often containing an amplifier or DAC digital-to-analog converter. This is more common with Raspberry Pi due to its processing power and operating system, but can also be achieved with Arduino for simpler WAV file playback. Applications: a door sensor that emits a chime when opened, a security system sounding an alarm, a smart bin playing a tune when it's full, or an appliance giving a spoken notification when a cycle completes. 4.2.3 Controlling power, relays. For IoT devices that need to control much larger appliances or power loads, a simple GPIO pin isn't enough. Relays. A relay is an electrically operated switch. Your low-power Arduino or Raspberry Pi creates a small electrical signal that electromagnetically closes or opens a separate, high-power circuit. Think of it as a small trigger that flips a much larger switch. This safely isolates your delicate electronics from the high voltages and currents found in household appliances. Applications: turning on a coffee maker remotely, controlling garden lights, managing the power supply to an irrigation pump, or enabling disabling a fan based on temperature readings. Relays are crucial for home automation projects aiming to control mains-powered devices. 4.2.4 Creating movement, motors and servos. To make things move, you need motors, and there are a few key types common in IoT projects. DC motors. These are the simplest motors, typically found in toys or small fans. When you apply power, they spin. Reversing the polarity, swapping the positive and negative connections, reverses the direction. They are controlled by varying the voltage, with higher voltage meaning faster rotation. For precise control, especially of speed, they are usually driven by a motor driver board. Servo motors. Servos are designed for precise angular positioning. Instead of continuous rotation, a servo motor typically rotates to a specific angular position, e.g., from 0 to 180 degrees, based on a control signal from your device. They maintain that position even when external forces try to move them. Stepper motors. Stepper motors excel at very precise, controlled movements. They move in discrete, exact steps, like 1.8 degrees per step. This makes them ideal for applications requiring exact positioning and repetition, like in 3D printers, CNC machines, or robotic arms. Applications: DC motors. Opening and closing blinds, controlling a small fan based on temperature. Servos. Opening a pet food dispenser, controlling a camera's pan and tilt mechanism, unlocking a smart door. Steppers. Automated curtains that open or close precisely to a certain point, positioning a sensor precisely in industrial applications. 4.3 Control methods. How your device drives actuators. Just as sensors send varying signals, your Arduino or Raspberry Pi needs different ways to send signals to actuators. Digital output on-off, the simplest control method. Many actuators, like LEDs or relays, are simply turned fully on or fully off by sending a high or low voltage signal to a GPIO pin. It's like flipping a light switch. Pulse width modulation, PWM. This is a clever technique used to simulate analog control using digital signals. Instead of providing a continuous, variable voltage, your device rapidly switches a digital pin on and off at a very high frequency. The width of the pulse, how long it stays on versus off within a cycle, determines the average power delivered. For example, if the signal is on for 50% of the time, the average power is half, making an LED appear dimmer, or a DC motor spin at half its maximum speed. PWM is crucial for controlling brightness, motor speed, and servo motor positions. Serial communication. For more complex actuators like LCD OLED displays or advanced motor drivers, you'll often use serial communication protocols like I2C, SBI, or UART, which we learned about in the sensor chapter. These protocols allow your device to send commands and data, e.g., display this text, rotate to 90 degrees, move 500 steps to the actuator, which then performs the requested action. Again, libraries will greatly simplify this by handling the low-level communication details. 4.4 Interfacing actuators with Arduino and Raspberry Pi. Connecting actuators often involves considerations beyond just plugging them into pins. Current requirements. Many actuators, especially motors, require more electrical current than a typical Arduino or Raspberry Pi GPIO pin can safely provide. Trying to draw too much current directly from a pin can damage your board. Solution. For high-current actuators, like most motors or relays, you'll use driver circuits or motor driver boards. These boards act as intermediaries. Your Arduino or Raspberry Pi sends a low-current control signal to the driver, and the driver, powered by an external power supply, then provides the necessary high current to operate the actuator. Just as we use libraries to simplify sensor reading, these driver boards often have their own libraries that make controlling them straightforward. Voltage levels. Ensure the voltage supplied to the actuator matches its requirements. While your Arduino or Pi might run on 3.3V or 5V, some actuators might need 12V or more. Driver circuits can also manage these voltage differences. Protection. Components like diodes are often used with motors to prevent back EMF, electromagnetic force, a brief surge of voltage that motors can generate when they stop spinning, which could damage your control circuit. Case study. Let's imagine we want to build a smart window opener. This device should sense rain and automatically close the window to prevent water damage. To achieve this, it would use a rain sensor, a type of sensor, and a small motor to move the window. Sensing, a rain sensor detects the presence of moisture. This sensor provides a digital output, no rain or rain detected. Processing, your Arduino or Raspberry Pi constantly monitors this rain sensor. Actuating, if the rain sensor indicates no rain, the window remains open or opens if it was previously closed. If the rain sensor indicates rain detected, the device sends a signal to a motor driver board. The motor driver then powers a small DC motor or stepper motor that is mechanically linked to the window, causing it to close. The system might also include a limit switch, another type of sensor, at the closed position to tell the motor when to stop and to ensure the window is fully closed. This example illustrates a full sensor-to-actuator loop, demonstrating how an IoT device responds intelligently to its environment using both sensing capabilities and physical action. 4.5 Tips for actuator selection and usage. Understand power requirements. Always check the voltage and current requirements of your chosen actuator before connecting it. If it needs more power than your control board can provide, plan to use an external power supply and a driver circuit. Match control method. Ensure the actuator's control method, digital, PWM, serial, is compatible with your Arduino or Raspberry Pi's capabilities and your programming logic. Mechanical considerations. If your actuator involves movement motors, servos, think about the mechanical linkage. Does it need gears, levers, or specific mounting? The physical integration is as important as the electronic one. Noise feedback. Motors can sometimes generate electrical noise that can interfere with sensitive sensor readings. Consider proper wiring, shielding, and power separation to mitigate this. Safety. Especially with high-power actuators like relays, ensure all connections are secure, insulated, and follow electrical safety guidelines. Never work with mains electricity without proper precautions or professional supervision. Conclusion and chapter summary. This chapter has introduced you to the world of actuators, the crucial components that enable your IoT devices to take physical action. We've covered various types, from simple visual indicators like LEDs and audible buzzers, to robust power controllers like relays, and devices that create movement such as DC, servo, and stepper motors. We also explored the different ways your Arduino or Raspberry Pi commands these actuators, from basic digital on-off signals to the more nuanced control offered by pulse width modulation and serial communication. Finally, we emphasized the practical considerations of current, voltage, driver circuits, and safety when integrating actuators into your projects. By combining the sensing capabilities discussed in the previous chapter with the acting capabilities of actuators, your IoT device can move beyond passive data collection to actively respond to and interact with its environment. But before we start building complex circuits, it's essential to understand the fundamental language that connects all these components: basic electronics. Our next chapter will delve into the essential electronic principles and prototyping techniques you'll need to make your interconnected components truly communicate. Chapter 5, The Language of Things, Basic Electronics and Prototyping. Up to this point, we've discussed the brains of your IoT device, Arduino and Raspberry Pi, its senses, sensors, and its actions, actuators. But how do all these pieces actually talk to each other? How do you ensure they receive the right amount of power without being damaged? The answer lies in understanding the fundamental language of electricity, basic electronics. Even if you're eager to jump straight into building, a solid grasp of these core concepts will save you immense frustration, help you troubleshoot problems, and enable you to design more robust and reliable IoT creations. 5.1 Fundamental Concepts, the ABCs of electricity. Electricity, at its simplest, is the flow of electrons. To understand how electronic components work, we need to grasp three fundamental concepts: voltage, current, and resistance. Voltage V, the push. Imagine a water pipe. Voltage is like the water pressure. It's the electrical pressure or potential difference that pushes electrons through a circuit. It's measured in volts. A higher voltage means a stronger push, leading to more potential for power. Your Arduino and Raspberry Pi typically operate at either 3.3 volts or 5 volts, which are low, safe voltages for hobbyist electronics. Current I, the flow. In our water pipe analogy, current is like the amount of water flowing through the pipe. It's the rate of flow of electrons past a given point in a circuit. It's measured in amperes, often shortened to amps or milliamps for small currents. Too much current flowing through a component can damage it, and too little might prevent it from working. Resistance, R. The opposition. Resistance is like the narrowness of the pipe or anything that obstructs the water flow. It's the opposition to the flow of current. It's measured in ohms. A component with high resistance will allow very little current to flow through it for a given voltage. Conversely, a component with low resistance will allow a lot of current to flow. These three concepts are intrinsically linked by Ohm's law, one of the most fundamental laws in electronics. Simply put, voltage V equals current I times resistance R. This means if you know any two values, you can calculate the third. For example, if you want a certain amount of current to flow through a component and you know its resistance, you can determine how much voltage is needed. Or, if you have a certain voltage and your component has a known resistance, you can calculate how much current will flow, which is crucial for preventing damage. 5.2 Common Components. The building blocks. Now that we understand the basic principles, let's look at some common electronic components that implement these ideas. Resistors. Purpose. As their name suggests, resistors resist the flow of current. They are used to limit current to a safe level for other components, like LEDs, which can burn out if too much current flows through them, or to divide voltage. They are usually small, colored bands indicate their resistance value. How to think about them? An LED needs just the right amount of current to light up brightly without burning out. A resistor placed in series with the LED acts like a tiny bouncer at a club, politely limiting the number of electrons that can pass through to the LED at any given moment. LEDs, light-emitting diodes. Purpose. As discussed in Chapter 4, these little lights emit light when current flows through them in the correct direction. They are polarized, meaning they have a positive and a negative leg. Connection note. Always use a resistor in series with an LED when connecting it to your Arduino or Raspberry Pi to limit the current and protect both the LED and the control board. Capacitors. Purpose. Capacitors store electrical energy in an electric field. Think of them as tiny, temporary batteries. Uses. They are often used to smooth out voltage fluctuations, filter out electrical noise, or store and release bursts of energy. In IoT, they might stabilize power to sensitive sensors or support communication lines. Transistors. Purpose. These are fundamental semiconductor devices that act primarily as electronic switches or amplifiers. As a switch, a small current or voltage applied to one part of the transistor can control a much larger current or voltage flowing through another part. How to think about them? Imagine a faucet. A tiny turn of the handle, small current, can control a much larger flow of water, larger current. This is incredibly useful for turning on higher current devices, like relays or small motors, with the low current signals from your Arduino or Raspberry Pi without needing a full-blown motor driver in some cases. Most modern integrated circuits, including the brains of your Arduino and Raspberry Pi, contain millions of tiny transistors. 5.3 Prototyping tools. Bringing your ideas to life. Before permanently soldering components together, you need a way to test your circuits. This is where prototyping tools become essential. Breadboards. Purpose. A breadboard is a rectangular plastic board with a grid of interconnected holes. It allows you to quickly build temporary electronic circuits without soldering, making it easy to experiment, connect components, and test your ideas. How they work. The holes in a breadboard are internally connected in rows and columns. Typically, the long rows along the sides, often marked with blue and red lines, are connected horizontally and are used for power supply, positive and negative rails. The shorter columns in the middle are connected vertically and are where you plug in individual components and jumper wires. Why they're great? They are indispensable for beginners as they allow you to rearrange components quickly, debug easily, and reuse parts without damage. Jumper wires. Purpose. These are simply wires with connectors on their ends designed to plug into breadboards, Arduino/Raspberry Pi pins, and sensor actuator headers. Types. They come in various lengths and often have male-to-male, female-to-female, or male-to-female connectors, allowing you to connect different types of pins. Multimeter basic use. Purpose. A multimeter is an incredibly useful diagnostic tool that can measure voltage, current, and resistance. Basic use. You can use it to check if your power supply is providing the correct voltage, e.g., 5V, to ensure continuity, that wires are properly connected and not broken, or to measure the resistance of a component. Understanding how to use the basic voltage, DC volts, and continuity functions on a multimeter will greatly aid in troubleshooting your projects. 5.4 Safe practices. Preventing shocks and shorts. Working with electronics, even low-voltage ones, requires adherence to basic safety practices to protect yourself and your components. Polarity matters. Pay attention to polarity. Diodes, including LEDs, many integrated circuits, capacitors, and power supplies are polarized. This means they must be connected the correct way, positive to positive, negative to negative. Connecting them backward can prevent them from working or even destroy them. Always look for markings, plus, or a flat edge on an LED indicating the negative side. Avoiding short circuits. A short circuit occurs when current finds an unintended, low-resistance path, often bypassing the component it's meant to power. This can lead to excessive current draw, overheating, component damage, or even fire. Prevention. Double-check your wiring on the breadboard. Ensure wires don't accidentally touch where they shouldn't. Keep stray strands of wire contained. Proper power connections. Always connect your power supply to the appropriate voltage input pins on your Arduino or Raspberry Pi boards. Using incorrect voltages, e.g., applying 12V to a 5V input not designed for it, can permanently damage the board. Power down before disconnecting. Whenever possible, disconnect power from your circuit before plugging in or unplugging components or repositioning wires. This reduces the risk of accidental short circuits or damaging components through hot plugging. Electrostatic discharge, ESD prevention. Static electricity buildup on your body can generate high voltages that, while harmless to you, can damage sensitive electronic components. Before handling delicate boards like a Raspberry Pi, touch a grounded metal object, like a radiator or the metal casing of a powered-off computer, to discharge any static. Work on a non-static surface if possible. 5.5 Conceptual troubleshooting of basic circuits. Despite your best efforts, circuits sometimes don't behave as expected. Here's a conceptual approach to troubleshooting. Check power. Is your Arduino or Raspberry Pi powered on? Are the power indicator lights on the board illuminated? Is the power supply providing the correct voltage? Use your multimeter for this. Verify connections. Review your breadboard wiring step-by-step against your circuit diagram or instructions. Are all wires securely plugged in? Is everything connected to the correct pins? Is polarity correct for components like LEDs? Is there an accidental short circuit where wires are touching? Test components individually, if possible. If you suspect a component is faulty, can you test it in a simpler circuit to confirm it works? For example, can you just light up an LED directly with a resistor and a battery? Confirm code logic for microcontrollers/microprocessors. If the hardware seems fine, is your code instructing the components correctly? Is it sending the right signals to the right pins? Tools like the Arduino serial monitor or Python print statements on Raspberry Pi can help you see if your code is executing as expected and if sensor readings are making sense. Simplify and isolate. If your circuit is complex, remove components one by one until you find the point where it starts working or where the problem becomes obvious. Start with the simplest possible circuit, e.g., just turning on a single LED, and build up from there. By understanding these fundamental electronic concepts, how components function conceptually, and how to safely prototype, you're building the essential foundation for creating reliable and functional IoT devices. The language of things isn't just about programming, it's also about speaking the language of electrons. Conclusion and chapter summary. This chapter has provided a foundational understanding of basic electronics, which is the vital language exchanged between all the components of your IoT device. We've simplified complex concepts like voltage, current, and resistance, linking them with the crucial Ohm's law. We then introduced key electronic components: resistors for current control, LEDs for visual feedback, capacitors for energy storage, and transistors as switches or amplifiers. Crucially, we explored the practical world of prototyping, highlighting the invaluable role of breadboards for temporary circuit assembly, jumper wires for making connections, and the basic functions of a multimeter for diagnosing problems. Finally, we covered essential safety practices, emphasizing polarity, avoiding short circuits, proper power connections, and guarding against electrostatic discharge, along with a conceptual framework for troubleshooting. With this solid groundwork in basic electronics and safe prototyping, you are now equipped to connect your sensors and actuators to your chosen brain. But for your IoT device to be truly connected, it needs to communicate with the wider world. In our next chapter, we will delve into the various communication protocols that enable your devices to send and receive data over networks, truly bringing them into the Internet of Things. Chapter 6. Speaking to the World. IoT Communication Protocols. Your IoT device has a brain, senses, and the ability to act. But for it to truly be part of the Internet of Things, it needs to communicate. It needs to send sensor data to a central system or the cloud, receive commands to activate actuators, or even talk to other nearby devices. This communication happens over various networks using specific languages, called communication protocols. Choosing the right one is crucial for your project's success, balancing factors like range, power consumption, data rate, and cost. 6.1 Overview of network types. From local to global. Before diving into specific protocols, let's understand the different scales of networks that IoT devices typically use. Personal Area Networks, PAN. These are very short-range networks, typically a few meters, designed for communication between devices around a single person. Think of your wireless headphones connecting to your phone. Bluetooth is a prime example. Local Area Networks, LAN. These networks cover a limited area, like a home, office, or small building. They offer higher data rates and are commonly used for connecting multiple devices within a confined space. Wi-Fi and Ethernet are the most common examples. Wide Area Networks, WAN. These networks span large geographical areas, connecting cities, regions, or even continents. They are essential for devices that need to send data over long distances without local network infrastructure. Cellular networks, like 4G, 5G, and newer low-power options like LoRaWAN, fall into this category. 6.2 Key wireless protocols for IoT. The language choices. The choice of communication protocol dictates how your device connects to the internet or other devices. Each has its strengths and weaknesses. 6.2.1 Wi-Fi. Ubiquitous and high bandwidth. How it works. Wi-Fi is probably the most familiar wireless technology, enabling devices to connect to the internet via a wireless router. It uses radio waves to transmit data over short to medium distances. Strengths for IoT. Ubiquitous infrastructure. Most homes and businesses already have Wi-Fi networks, making integration straightforward. High bandwidth. Suitable for transmitting larger amounts of data, like video streams from a security camera or frequent sensor readings. Direct internet access. If your router is connected to the internet, your Wi-Fi-enabled IoT device can often directly communicate with cloud services. Weaknesses for IoT. Higher power consumption. Compared to other IoT-specific protocols, Wi-Fi is relatively power-hungry. This makes it less ideal for battery-operated devices that need to last for months or years. Limited range. While fine for a home or office, its range is limited outdoors or in large industrial environments without many access points. When to use. Smart home devices that are always plugged in, e.g., smart plugs, complex home hubs, video streaming devices, or any IoT device that needs to transfer significant amounts of data frequently. Many ESP32 and ESP8266 Arduino-compatible boards have built-in Wi-Fi, as do Raspberry Pi models. 6.2.2 Bluetooth BLE. Short range and low power. How it works. Bluetooth is a short-range wireless technology designed for direct device-to-device communication. It creates a personal area network. Bluetooth Low Energy, BLE, a newer version, is optimized for very low power consumption while maintaining reliable connections over short distances. Strengths for IoT. Very low power, BLE. Excellent for battery-powered devices like wearables, beacons, or health monitors that need to operate for long periods on small batteries. Direct device-to-device. Allows your phone to directly connect to and control a nearby IoT device without needing a Wi-Fi router. Secure, built-in security features. Weaknesses for IoT, limited range. Typically effective only within a few tens of meters. Lower data rate. Not suitable for high-bandwidth applications like video. Limited network topology, generally designed for one-to-one or one-to-few connections, not a large mesh network of devices directly talking to each other. When to use. Wearable fitness trackers, smart locks that communicate with your smartphone, proximity beacons, or simple control of nearby devices from a mobile app. Many Arduino boards can be augmented with Bluetooth modules, and most Raspberry Pi boards have built-in BLE. 6.2.3 LoRa WAN. Long range, very low power. How it works. LoRa long range is a modulation technique that allows very long-range communication at very low power. LoRaWAN, LoRa Wide Area Network, is a standardized network protocol built on top of LoRa, providing the communication architecture, security, and scalability for a wide area network. Devices connect to gateways, which then connect to the internet. Strengths for IoT: exceptional long range, can transmit data over several kilometers in rural areas and several hundred meters in dense urban environments. Extremely low power consumption. Devices can operate on small batteries for years, making it ideal for remote sensors. Good for small data packets, perfect for sending small, intermittent sensor readings, e.g., once an hour. Weaknesses for IoT: low data rate, not suitable for large data transfers or real-time streaming. Requires gateway infrastructure. You need LoRaWAN gateways in range to connect your devices to the internet. While community networks exist, you might need to deploy your own. When to use: remote environmental monitoring, e.g., forest fire detection, water level monitoring; smart agriculture, soil moisture sensors in fields miles away; asset tracking in large industrial complexes; or smart city applications like remote parking sensors or waste bin monitoring. 6.2.4 Cellular, 2G, 4G, 5G, NB IoT LTE-M. Ubiquitous and high reign. How it works: IoT devices use the same cellular networks that your mobile phone uses to connect to the internet. Newer cellular standards like narrowband IoT, NB-IoT, and LTE-M are specifically optimized for IoT devices, offering lower power consumption and lower costs compared to standard 4G, 5G. Strengths for IoT: global coverage. Leveraging existing mobile phone network infrastructure, cellular IoT provides very wide geographic coverage wherever there's a cell signal. Reliable and secure. Networks are managed by mobile carriers, offering robust security and reliability. High throughput, 4G, 5G. Standard cellular connections can handle high data rates, including video. Weaknesses for IoT: subscription costs. Requires a SIM card and a data plan, adding ongoing operational costs. Higher power consumption, standard cellular. While NB IoT LTE-M are low power, standard 4G, 5G modules can be power hungry, making them less suitable for long-term battery-only operation. Complexity, cost of modules. Cellular modules can be more complex and expensive than Wi-Fi or Bluetooth modules. When to use: fleet tracking, remote asset monitoring, e.g., shipping containers, industrial equipment in remote areas; smart metering, or any application where a device needs to send data from virtually any location. 6.3 IoT-specific data protocols, the language of data exchange. Once a device is connected to a network, it still needs a common language to exchange actual data efficiently. Here are two of the most popular data protocols in IoT. 6.3.1 MQTT, Message Queuing Telemetry Transport. Lightweight Publish Subscribe. How it works: MQTT is a lightweight messaging protocol designed for constrained devices and low bandwidth, high latency, or unreliable networks. It uses a publish-subscribe model. Publisher: an IoT device, e.g., a temperature sensor, publishes data to a specific topic, e.g., home living room temperature. MQTT broker: a central server, the broker, receives these messages and distributes them. Subscriber: any device or application, e.g., a smartphone app, a web dashboard, an actuator, that is subscribed to that topic will receive the message. Strengths for IoT: extremely lightweight, minimal overhead, making it efficient for resource-constrained devices. Asynchronous: devices don't have to wait for a response, making it fast and efficient. Many-to-many communication: a single message can easily be sent to multiple subscribers. Robust: built-in quality of service levels ensure message delivery reliability. When to use: ideal for almost any IoT application where devices send small amounts of data sporadically, sensor readings, or receive simple commands, turn light on off. It's widely supported by cloud IoT platforms and is excellent for communication between device and cloud. 6.3.2 HTTP REST, Request Response, Web Standard. How it works: HTTP, Hypertext Transfer Protocol, is the foundation of the World Wide Web. It operates on a request-response model. A client, your IoT device, makes a request, e.g., send this sensor data, and a server responds, e.g., data received. REST, Representational State Transfer, is an architectural style built on HTTP, making it a very common way for web services to interact. Strengths for IoT: universally supported. Web browsers, servers, and many programming languages natively understand HTTP, making integration with existing web services straightforward. Simple to understand. The request-response model is intuitive. Weaknesses for IoT: heavier overhead. HTTP messages are generally larger than MQTT, consuming more bandwidth and power per message. Synchronous. The client typically waits for a response from the server, which can introduce latency. Not ideal for push notifications. While servers can respond, they can't inherently push unsolicited messages to devices as easily as an MQTT broker can. When to use: devices that primarily upload data intermittently to a web server, e.g., a weather station sending data every few minutes, devices that need to interact with existing web APIs, or devices capable of running more powerful processors like a Raspberry Pi, where bandwidth and overhead are less of a concern. 6.4 Role of IoT gateways, translators, and hubs. Sometimes, simpler IoT devices, like those using Bluetooth or just basic wired sensors, don't have direct internet access. This is where an IoT gateway comes in. How it works: a gateway is a physical device or a software application that acts as a bridge between IoT devices and the cloud internet. It can collect data from local devices using various protocols, e.g., Bluetooth, Zigbee, LoRa, and then translate and forward that data to the internet using a different, generally higher bandwidth protocol like Wi-Fi or Ethernet. Functions: protocol translation, converts data from one protocol to another. Data aggregation, collects data from many local devices before sending it upstream, reducing network traffic. Edge processing, can perform local data filtering, analysis, or decision-making, reducing cloud load and improving response times. Security, can act as a local firewall or authentication point. When to use: in a smart home, a central hub, often a Raspberry Pi, could be a gateway connecting multiple low-power Zigbee light bulbs to your Wi-Fi network and then to a cloud service. In an industrial setting, a gateway might collect data from dozens of local sensors and then send aggregated, filtered data to a corporate network. Case study: imagine building a remote weather station. You want to measure temperature, humidity, and barometric pressure in a remote field, miles from any Wi-Fi. Solution: you could use an Arduino-compatible board with a LoRa module for the weather station itself. This device would collect readings and then use the LoRa protocol to send small data packets every hour or so. Miles away, a Raspberry Pi equipped with a LoRa gateway module and connected to the internet via Wi-Fi or Ethernet would receive these LoRa packets. This Raspberry Pi would then act as a gateway, translating the LoRa data and publishing it to an MQTT broker in the cloud. Your smartphone app could then subscribe to that MQTT topic and receive the real-time weather updates. This leverages LoRa's long range and low power for the remote device, and the Raspberry Pi's versatility as a gateway to bridge it to the internet using a more common web protocol like MQTT. Conclusion and chapter summary: choosing the right communication protocol is a critical decision in IoT design, often dictating the range, battery life, cost, and overall performance of your device. We've explored the landscape from short-range personal area networks, like Bluetooth BLE, to local ones Wi-Fi, and wide-area options, LoRaWAN cellular. We also distinguished between network physical protocols and the data exchange protocols, specifically contrasting the lightweight, publish-subscribe nature of MQTT with the ubiquitous, request-response model of HTTP REST. Finally, we saw how IoT gateways bridge these communication gaps, enabling simpler devices to connect to the broader internet. With a device that can sense, act, and speak to the world, the next crucial step is to understand what happens to all that data once it leaves your device. Our next chapter will delve into the cloud connection, exploring how data is stored, analyzed, and visualized, transforming raw sensor readings into meaningful insights and allowing you to interact with your IoT system remotely. Chapter 7: The Cloud Connection, storing, analyzing, and visualizing data. Your IoT device is now a master of communication, sending out data and receiving commands. But where does all that information go? and how does it become truly useful for humans or other systems? This is where the cloud connection becomes vital. The cloud, in the context of IoT, is a vast network of servers, databases, and software services managed by third-party providers, like Amazon Web Services, Microsoft Azure, Google Cloud, or even simpler platforms like Adafruit.io that store, process, and manage your IoT data. 7.1 Why use the cloud for IoT? You might wonder why you can't just store all data locally on your device or a home server. While local storage is possible for some applications, the cloud offers compelling advantages that address the unique challenges of IoT. Scalability. IoT devices can generate enormous amounts of data. The cloud provides virtually limitless storage and processing power that can scale up or down based on your needs, eliminating the worry of running out of space or computational resources. Accessibility. Once data is in the cloud, it can be accessed from anywhere in the world with an internet connection, on any device, smartphone, tablet, desktop. This enables remote monitoring and control of your IoT devices. Data processing and analytics. Cloud platforms offer powerful tools for analyzing vast datasets. This allows you to extract meaningful insights, identify patterns, detect anomalies, and even run machine learning models on your sensor data, turning raw numbers into actionable intelligence. Reliability and redundancy. Cloud providers offer highly reliable infrastructure with built-in redundancy, meaning your data is backed up and available even if a server experiences an issue. Managed services. Cloud platforms provide pre-built services specifically designed for IoT, simplifying tasks like device registration, message routing, data storage, and user authentication, reducing the need for you to build these complex systems from scratch. 7.2 Key Cloud Functions for IoT, a high-level view. While specific services vary between platforms, most IoT cloud solutions offer a set of core functionalities. Device registration and management. Before a device can send data to the cloud, it needs to be identified and securely connected. Cloud platforms provide mechanisms to register your devices, assign unique IDs, and manage their authentication credentials. Message queues brokers. This is the entry point for data coming from your devices. As we discussed in Chapter 6, often this involves an MQTT broker. These brokers efficiently receive data streams from thousands or millions of devices, ensuring messages are not lost and are routed to the correct destination. Data storage databases. Once messages are ingested, the raw sensor data needs to be stored. Cloud platforms offer various database options tailored for IoT data, such as time series databases that are optimized for storing data collected over time, e.g., temperature every minute. Rules engines logic. This allows you to define automated actions based on incoming data. For example, if temperature reading from sensor X exceeds 30 degrees Celsius, then send an alert email. These rules can also trigger commands back to devices, e.g., turn on the fan. Analytic services. After raw data is stored, it can be processed and analyzed. This might involve simple aggregations, average temperature over an hour, or complex algorithms like machine learning to predict equipment failure or optimize energy usage. Visualization and dashboards. To make sense of all the data, cloud platforms provide tools to create interactive dashboards, graphs, and charts. This allows users to easily monitor device status, visualize trends, and gain quick insights without needing to delve into raw data. Application Programming Interfaces, APIs. APIs allow you to programmatically interact with the cloud platform. This means you can build custom mobile apps, web applications, or integrate your IoT data with other business systems. 7.3 Introduction to Beginner-Friendly IoT Platforms. For those starting their IoT journey, there are several platforms that simplify the cloud connection process, offering free tiers and intuitive interfaces. Adafruit.io, what it is? Adafruit.io is a cloud service designed by Adafruit, a popular electronics company. It's incredibly user-friendly and well-documented, making it an excellent choice for beginners. How it works. You create feeds on Adafruit.io, e.g., a temperature feed, a light toggle feed. Your Arduino or Raspberry Pi device then publishes data to these feeds using MQTT or HTTP. You can create dashboards with various widgets, gauges, graphs, toggles, buttons to visualize your data or control your devices remotely. It also supports triggers for basic automation, allowing you to set up actions when certain conditions are met, e.g., if temperature rises above a certain point. Key benefit: its simplicity and clear integration with Arduino and Raspberry Pi. ThingSpeak. What it is? ThingSpeak is an open-source IoT analytics platform service developed by MathWorks, the creators of MATLAB. It allows you to analyze and visualize live data streams. How it works: similar to Adafruit I/O, you create channels for your data. Your device sends data to these channels, often using HTTP GET requests. ThingSpeak offers built-in MATLAB analysis functions, allowing for more advanced computations directly on the platform. It also provides tools for creating interactive visualizations. Key benefit: its integration with MATLAB for data analysis and slightly more advanced plotting capabilities without needing external tools. These platforms are invaluable for learning because they abstract away much of the complexity of setting up server infrastructure, allowing you to focus on getting your devices connected and seeing your data come to life. For those interested in scaling up or exploring more industrial applications, there are also enterprise-grade cloud IoT services from major providers. AWS IoT, Amazon Web Services, IoT. A comprehensive suite of services covering device connectivity, data processing, analytics, and security. Highly scalable and versatile. Azure IoT, Microsoft Azure IoT. Another robust platform offering similar capabilities to AWS IoT, with strong integration into Microsoft's enterprise ecosystem. Google Cloud IoT. Google's offering, known for its powerful data analytics and machine learning integration. These enterprise platforms offer immense power and flexibility, but come with a steeper learning curve and can incur significant costs for high-volume usage. For practical and learning purposes, platforms like Adafruit I/O and ThingSpeak are ideal. 7.4 Conceptual process of sending data from a device to the cloud and receiving commands back. Let's walk through the conceptual flow of how data moves from your device to the cloud and how commands travel back. This is the essence of a two-way IoT communication system. Sending data, device to cloud. Sensor reading. Your Arduino or Raspberry Pi reads data from a sensor, e.g., temperature and humidity. Data formatting. The device formats this raw data into a structured message, often in a lightweight format like JSON, JavaScript Object Notation, which is a human-readable and machine-parsable format, e.g. Temperature, 23.5, humidity, 60. Communication protocol. The device uses a chosen communication protocol, e.g., Wi-Fi plus MQTT or Wi-Fi plus HTTP, to send this message. MQTT example. The device publishes the JSON message to a specific MQTT topic on your cloud platform's MQTT broker, e.g., publishing to topic myhouse/sensor1/data. HTTP example. The device makes an HTTP post request to a specific URL on the cloud platform, sending the JSON message in the request body. Cloud ingestion. The cloud platform's message queues or ingestion services receive the message. Rules engine processing. A rules engine checks the incoming message. If the message meets certain criteria, e.g., temperature 25 degrees, it might trigger an action, like storing the data in a database, sending an alert, or even forwarding the message to another cloud service for further analysis. Data storage. The data is stored in a suitable database in the cloud. Visualization. Data from the database is pulled by dashboards or charting tools, allowing you to see real-time graphs and historical trends. Receiving commands, cloud to device. User interaction automation. A user clicks a button on a web dashboard, e.g., turn on light, or a rule in the cloud, e.g., if outside light level is low, turn on porch light, is triggered. Command generation. The cloud platform generates a command message. Communication protocol backwards. The command message needs to reach the device. MQTT example. The cloud platform publishes the command as a message to an MQTT topic that the device is subscribed to, e.g., publishing to topic myhouse/lights/porch/command with a message, on. HTTP example. This is often done by a polling mechanism where the device periodically sends an HTTP GET request to the cloud platform, effectively asking, "Are there any new commands for me?" The cloud platform would then respond with any pending commands. MQTT's publish-subscribe model is generally more efficient for command and control as the device doesn't need to constantly ask. Device reception. The Arduino or Raspberry Pi, which is continuously connected and either subscribed to the command topic, MQTT, or polling for commands, HTTP, receives the command message. Actuator action. The device parses the command message, e.g., on for porch light, and then triggers the appropriate actuator, e.g., sends a signal to the GPIO pin connected to the porch light's relay, turning it on. Practical application example. Using Adafruit I/O, you would conceptually create a feed, name it bedroom temp for sensor data and bedroom light control for commands. Program your device. Write code for your Arduino or Raspberry Pi to read the temperature sensor. Connect to Adafruit I/O via Wi-Fi and MQTT. Publish the temperature reading to the bedroom temp feed. Subscribe to the bedroom light control feed to listen for commands. When a message like on or off is received on bedroom light control, activate or deactivate an LED or a relay for a real light. Create a dashboard. On the Adafruit I/O web interface, drag and drop a line chart widget for bedroom temp to visualize the temperature history. Add a toggle button widget for bedroom light control that sends on or off messages when clicked. Through this simple setup, you've created a complete IoT system from sensor to cloud to user interface and back to actuator control. Conclusion and chapter summary. The cloud is an indispensable component of modern IoT systems, providing the scalability, accessibility, and analytical power necessary to manage and derive value from vast amounts of sensor data. We explored the core functions offered by cloud platforms, including device management, data ingestion, storage, analytics, and visualization. We also highlighted beginner-friendly options like Adafruit I/O and ThingSpeak, which simplify the learning process before diving into professional-grade services like Oz IoT or Azure IoT. Crucially, we detailed the conceptual flow of data from your device to the cloud and how commands travel back, enabling two-way communication and remote control. Connecting to the cloud transforms your individual connected devices into a cohesive, intelligent system. You now have the knowledge of how to sense, act, speak, and connect to the internet. The next step is to put all these pieces together systematically. In Chapter 8, we will explore the practical IoT project workflow, guiding you through the steps from ideation and component selection to bringing your connected ideas to life. Chapter 8, Bringing Ideas to Life, the IoT project workflow. You now have a solid understanding of the individual components of an IoT system: the brain, Arduino/Raspberry Pi, the senses, sensors, the actions, actuators, and the communication pathways to the wider world, protocols, and cloud. The real magic happens when you bring these pieces together to create a working, intelligent device. This chapter outlines a systematic workflow for transforming your abstract IoT idea into a tangible, functional prototype. 8.1 From Idea to Prototype, a structured approach. Building an IoT device is usually an iterative process. You won't get everything perfect on the first try, and that's expected. A structured workflow helps you break down a large project into manageable steps, making the process less daunting and more efficient. 8.1.1 Problem Definition and Ideation. Every effective IoT project starts with a clear idea or a problem to solve. Instead of starting with, "I want to build an IoT device," begin with, "What problem can a connected device solve?" Or, "What task can be automated or improved?" Brainstorm. Think about your daily routines, common frustrations, or areas where data could provide valuable insights. Do you constantly forget to water your plants? Wish you knew if your dog was barking while you were out? Or want an easier way to monitor your home's air quality? Define the SMART aspect. How does connecting this device to the internet make it better than a traditional, unconnected solution? Does it enable remote access, data logging, automation, or integration with other services? 8.1.2 Feasibility Assessment. Can I build this? Once you have an idea, perform a quick reality check. Technical feasibility. Do the necessary sensors and actuators exist? Can they integrate with your chosen platform, Arduino/Raspberry Pi? Are the communication protocols available in your environment? Knowledge gaps. What do you need to learn? Don't be afraid if there are many unknowns. That's part of the learning process. But be realistic about what you can achieve. Cost and time. Roughly estimate the budget for components and the time commitment for building and programming. 8.1.3 Component Selection Process. Based on your problem definition and feasibility assessment, start listing the exact components you'll need. This is where your knowledge from previous chapters comes into play. Choose the brain, Arduino or Raspberry Pi, or a combination. Base this on the complexity of logic, processing power needed, and power constraints. Identify sensors. What inputs do you need? E.g., temperature, motion, light, soil, moisture. Research specific models, e.g., DHT11, HCSR04, LDR. Identify actuators. What outputs do you need? E.g., LED, buzzer, relay, servo motor. Connectivity modules, which wireless technology? E.g., Wi-Fi module, LoRa module, cellular shield. Auxiliary components. Do you need resistors, jumper wires, a breadboard, power supplies, or motor drivers? Enclosure. How will you house your final device? Will it be weatherproof, discreet? 8.1.4 Conceptual Circuit Design. Before connecting wires, draw a simple diagram or verbally map out your connections. This doesn't have to be a formal schematic for a beginner, but a clear plan. Which pins go where? E.g., DHT11 data pin to Arduino digital pin 2. Servo signal wire to Raspberry Pi GPIO 18. Power connections. Where do component power and ground connect? Resistors needed? E.g., for LEDs or pull-up pull-down resistors for some digital inputs. 8.1.5 Building the physical prototype. Start assembling your device using a breadboard. Start small, begin with the core functionality. For example, if you're building a weather station, first get just the temperature sensor working and reliably sending data. Incremental build. Add components one by one. Test each new component as you add it. This makes debugging much easier. If something goes wrong, you know it's likely related to the last component you added or its connections. Neat wiring as much as possible. While prototyping, it's easy to create a spaghetti of wires. Try to keep wires organized, use different colors for power ground data, and cut jumper wires to a suitable length. This makes troubleshooting much simpler. 8.1.6 Developing the device logic. This is where you bring your programming skills into play. While we won't show code blocks, let's describe the conceptual flow of a program. Setup phase. When your device first powers on, it needs to initialize. This often involves setting up pins as inputs or outputs, configuring communication protocols, like connecting to Wi-Fi or initializing an MQTT client, and setting initial states for actuators, e.g., ensuring a light is off. Loop phase for MCUs or main program for MPUs. This is where the core logic resides. Read sensors. The program periodically reads data from your sensors. For instance, read the temperature from the DHT11 sensor every 5 seconds. Process data, make decisions. Based on sensor data, the program makes decisions. This involves using conditional statements if-else. For example, if the temperature is above 25 degrees Celsius. Control actuators. Based on decisions, the program controls actuators. Then turn on the fan, send high signal to GPIO pin connected to fan's relay. Communicate. Send data to the cloud or receive commands. Publish the temperature data to the cloud via MQTT. Check if there's a new command from the cloud to turn on the light. Wait delay. Implement pauses to avoid overwhelming the system or to save power. Using libraries. Leverage libraries whenever possible. Instead of writing complex code to interpret raw data from an ultrasonic sensor, a library allows you to simply call a function like ultrasonic get distance cm. 8.1.7 Testing and debugging strategies. Troubleshooting is an inescapable part of electronics and programming. Serial monitor console output. Both Arduino IDE and Raspberry Pi, Python, allow you to print messages to a serial monitor or console. This is invaluable. Use it to print sensor readings, confirmation messages, Wi-Fi connected, or variable values to understand what your device is thinking. This visual feedback helps you trace the program's execution and identify where things go wrong. LED indicators. Use simple LEDs as visual debuggers. A blinking LED might indicate data sent, while a solid LED might mean error connecting. Break down the problem. If a complex system isn't working, isolate the problem. Is it the hardware, the software, the connectivity? Can the sensor be read reliably? Can the actuator be controlled directly? Can the device connect to Wi-Fi? Can it send a simple message to the cloud? If all individual pieces work, the problem is likely in their integration. Consult documentation and community. Official documentation, online forums, and community tutorials are treasure troves of solutions to common problems. 8.1.8 Iteration and Refinement. Your first prototype will rarely be perfect. Test thoroughly, test under different conditions for extended periods. Identify weaknesses. Is the sensor sometimes inaccurate? Does the Wi-Fi disconnect? Is the battery life too short? Refine and improve. Make changes, retest, optimize code, improve power management, design a better enclosure. This cycle is crucial for moving towards a reliable and robust IoT device. 8.2 Detailed Project Walkthrough. Conceptual. A smart pet feeder. Let's apply this workflow using a specific project idea. A smart pet feeder. 8.1.1 Problem Definition. My pet gets hungry when I'm away, and I often forget to fill the feeder or stick to a strict schedule. I want a feeder that can dispense food automatically, tell me when it's running low, and be controllable remotely. 8.1.2 Feasibility. Sensors. An ultrasonic sensor can measure food level. Actuator. A servo motor can open-close a chute to dispense food. Connectivity. Wi-Fi for remote control and cloud communication. Brain. A Raspberry Pi would be good to manage scheduling, remote control, and possibly even a small camera feed. But for a simpler version, an ESP32, Arduino compatible with Wi-Fi, could suffice. Let's aim for the ESP32 for simplicity and low power for this example. Likely components exist, programming is feasible. 8.1.3 Component Selection. Brain. ESP32 development board, built-in Wi-Fi. Sensor. HCSR04 ultrasonic distance sensor, measures distance to food level. Actuator. Standard servo motor e.g., SG90 or MG996R, depending on required torque for the food gate. Power, small power supply e.g. 5V USB adapter, suitable for the ESP32 and servo. Prototype, breadboard jumper wires. Cloud. Adafruit I/O for cloud integration. 8.1.4 Conceptual Circuit Design. ESP32 Power. Connect 5V power supply to the ESP32's 5V VIN pin and ground. Ultrasonic sensor. VCC to ESP32 5V or 3.3V, check sensor spec. GND to ESP32 GND. Trigger pin to a specific ESP32 GPIO pin, e.g., GPIO 23. Echo pin to a specific ESP32 GPIO pin, e.g., GPIO 22. Servo motor. Power red wire to ESP32 5V ground brown-black wire to ESP32 GND. Signal orange-yellow wire to a specific ESP32 GPIO pin capable of PWM, e.g., GPIO 18. Note: for more demanding servos, a separate power supply with common ground might be needed to avoid browning out the ESP32. 8.1.5 Building the physical prototype. Simplified description. Connect the ESP32 to basic power. Confirm it powers on. Add the ultrasonic sensor to the breadboard, wire it to the ESP32's chosen pins. Add the servo motor, wire its power, ground, and signal to the ESP32. Temporarily attach a simple food gate mock-up to the servo horn. 8.1.6 Developing the device logic, conceptual program flow. Setup phase. Initialize serial communication for debugging output. Connect to Wi-Fi using your network name and password. Initialize the ultrasonic sensor library. Initialize the servo motor library and attach it to the correct pin. Connect to Adafruit I/O via MQTT, providing your username and API key. Subscribe to a specific Adafruit I/O feed, e.g., UFeed's food dispense command, to listen for remote dispense requests. Loop phase runs continuously. Read food level. Every minute or some interval, instruct the ultrasonic sensor to measure the distance to the food. The sensor sends out sound waves, the program times the return of the echo, and calculates the distance in centimeters. Self-correction logic. If the distance is greater than 10 cm, meaning food is low, update the food level feed on Adafruit I/O with low. Otherwise, update with OK. Print this to the serial monitor. Dispense food, scheduled. Maintain a variable for last dispensa time. If current time is past 8 o'clock a.m. and last dispensa time was more than 23 hours ago and the food level is OK, then activate the servo motor. Move it to the open position, e.g., 90 degrees, pause for 2 seconds to let food fall, then move it back to the closed position, e.g., 0 degrees. Update last dispensa time to current time. Publish a message to Adafruit I/O. Food dispensed automatically. Print this to serial monitor. Dispense food, remote command, continuously check if a message has been received on the food dispense command feed. If the message received is dispense now, then activate the servo motor. Move to open, pause 2 seconds, move to closed. Publish a message to Adafruit I/O, food dispensed remotely. Print this to serial monitor. Maintain connection. Ensure the Wi-Fi and MQTT connections to Adafruit I/O remain active. If disconnected, attempt to reconnect. 8.1.7 Testing and debugging. Serial monitor. Use it constantly. Print distance values from the ultrasonic sensor. Print Wi-Fi connected. Messages. Print MQTT connected disconnected status. Print servo moving action. Messages. Print command received. X when Adafruit I/O sends a command. LED check. Use the ESP32's built-in LED, if available, to signal Wi-Fi connection status or when a dispense action is triggered. Manual servo test. First, write a tiny program to just run the servo motor through its open-close sequence directly, confirming the mechanical part works without the sensor or cloud logic. Cloud dashboard. Watch the Adafruit I/O dashboard. Does the food level update correctly? Do commands sent from the button widget get received by the device? 8.1.8 Iteration and refinement. Food level accuracy. Is the ultrasonic sensor consistently measuring the food level? Does the container shape affect accuracy? Adjust the placement or the math if needed. Dispensing reliability. Does food always dispense when the servo moves? Is the servo strong enough? Adjust settings or the mechanical assembly. Power efficiency. If battery-powered, look into putting the ESP32 into deep sleep between readings to conserve power. Failure modes. What happens if the Wi-Fi drops? Does it try to reconnect? What if the servo jams? How is that handled? User experience. Is the remote control intuitive? Are notifications clear? This conceptual walkthrough demonstrates how each step of the workflow contributes to building a functioning IoT device, emphasizing that it's a process of planning, building, coding, testing, and refining. Conclusion and chapter summary. This chapter has provided a practical, step-by-step workflow for bringing your IoT ideas to life. We began with the critical steps of problem definition and feasibility assessment, moving into the systematic selection of components, conceptual circuit design, and the incremental process of physical prototyping. We then deeply explored the development of device logic, emphasizing the setup and loop phases, conditional statements, and the use of libraries. Crucially, we covered essential testing and debugging strategies, highlighting how observation, serial monitor output, and LED indicators can help you troubleshoot. Finally, we emphasized the iterative nature of the process, learning, refining, and improving your prototype. The conceptual walkthrough of building a smart pet feeder demonstrated how all the elements from previous chapters come together in a real-world application. You now possess a comprehensive roadmap for transforming an idea into a working IoT prototype. However, A significant part of ensuring your device is practical and lasts is its power supply. Our next chapter will delve into the critical aspects of powering your projects, exploring various power sources and strategies for energy management, an often overlooked but vital part of IoT design. Chapter 9. Powering your projects, energy management for IoT devices. You've designed your IoT device, connected its sensors and actuators, established its communication to the cloud, and even walked through the prototyping process. But what brings it to life? What keeps it running day after day, year after year? The answer, often overlooked until frustration sets in, is a reliable and efficient power supply. Power management is a critical aspect of IoT design. A well-designed, functional prototype is useless if it runs out of battery in a few hours or demands an inconvenient power connection. 9.1 Understanding power. Voltage, current, and consumption. Let's briefly revisit our foundational electronics concepts with a focus on power in the context of IoT voltage, V. The electrical pressure. Most Arduino boards typically operate at 5V, while Raspberry Pi boards and newer microcontrollers often use 5V or 3.3V. Components are designed for specific voltage levels. Current, A or MA, the flow of electricity. Different components draw different amounts of current. Sensors might draw milliamps, MA, while motors or Wi-Fi modules can draw hundreds of milliamps or even amps. Power, W, the rate at which energy is consumed or produced. It's the product of voltage and current. Power, watts, equals voltage, volts, times current, amps. A device drawing 100 mA, 0.1 A, at 5V consumes 0.5 watts. A device drawing 500 mA, 0.5 A, at 5V consumes 2.5 watts. Understanding power consumption is crucial for estimating battery life or sizing your power supply. 9.2 Common power sources for IoT projects. The choice of power source depends heavily on your project's location, required runtime, and power needs. USB power. How it works. Many Arduino and Raspberry Pi boards can be powered directly via a standard USB cable connected to a computer, a USB wall adapter, like a phone charger, or a USB power bank. USB typically provides 5V pros, convenient, readily available, standard for development and many indoor projects. Cons, not suitable for long-term outdoor deployment without an outdoor-rated power supply, cable length limitations, requires a constant power outlet. Battery types, when your device needs to be portable, remote, or operate without a wall outlet, batteries are essential. AAA batteries, simple, widely available, easy to replace. Typically 1.5V per cell alkaline or 1.2V Ni-mH rechargeable. You often need multiple in series to achieve the required voltage, e.g., 3 AA batteries for 4.5V. LiPo lithium polymer and Li-ion lithium-ion batteries. High energy density, more power in a smaller, lighter package, rechargeable. A single LiPo cell provides 3.7V nominal. Common in portable electronics. Important note: LiPo batteries require special charging circuits and careful handling, as they can be a fire hazard if short-circuited, overcharged, or overdischarged. Always use a dedicated LiPo charger. 18,650 batteries, a common type of rechargeable Li-ion battery, often found in laptop battery packs or larger power banks. Offers good capacity. Coin cell batteries, CR2032, very small, low capacity. Suitable only for extremely low power devices that need to run for a very long time, like small, intermittent Bluetooth beacons that transmit data once a day. Solar panels, how it works. Solar panels convert sunlight into electrical energy. They are often paired with a rechargeable battery and a charge controller circuit. Pros: renewable energy, ideal for remote outdoor deployments where running power lines is impractical. Can achieve very long operating times if sized correctly. Cons: requires sunlight, output varies with weather and time of day, requires a charge controller, cost of panel and battery. AC adapters/wall warts. How it works. These are simple power supplies that plug into a wall outlet and convert alternating current, AC, household power into suitable direct current, DC voltage for your device, e.g. 5V, 9V, 12V. Pros: consistent power, easy to use for stationary indoor projects. Cons: requires a wall outlet, not portable. 9.3 Measuring power consumption, conceptual use of a multimeter. To understand your device's power draw, you need to measure its current consumption. While a professional current meter is best, a standard multimeter can give you a good estimate. Conceptual method: set your multimeter to measure current amps or milliamps. Break the circuit path between your power source and your device. Insert the multimeter in series with the circuit. This means all the current flowing to your device must pass through the multimeter. The multimeter effectively becomes part of the wire. Read the current on the multimeter display. Caution: never connect a multimeter set to measure current in parallel across power leads, like connecting it directly across your power supply terminals. This will create a short circuit and likely blow a fuse in your multimeter or damage your power supply. Knowing the device's average current draw is usually sufficient to estimate battery life. Battery life calculation, simple estimation. Battery capacity. Batteries are rated in milliamp hours, mAh, or amp hours, Ah. This indicates how much current they can supply for a certain duration. A 2000 mAh battery can supply 2000 mAh for 1 hour or 100 mAh for 20 hours. Formula: estimated battery life hours equals battery capacity, mAh, average current draw, mAh. Example: if your device draws an average of 50 mAh and you're using a 2000 mAh battery, the estimated life is 2000 mAh/50 mAh equals 40 hours. This is a rough estimate. Real-world conditions like temperature, battery age, and peak current draws can affect actual life. 9.4 Strategies for efficiency. Making your power last. For battery-powered IoT devices, maximizing energy efficiency is paramount. Choosing efficient components. Start by selecting components known for low power consumption. For instance, some sensors and microcontrollers are specifically designed for low power operation. Using sleep modes. This is arguably the most effective technique for reducing power consumption in microcontrollers like Arduino and ESP32. How it works. Instead of running continuously, the microcontroller can enter various sleep states where it powers down most of its internal components, only waking up periodically, e.g., once every 5 minutes to perform its task. Read sensor. Send data before going back to sleep. Example: an Arduino-based weather station might only wake up every 10 minutes to read sensors, transmit data, and then enter deep sleep for the remaining 9 minutes and 50 seconds. During deep sleep, current draw can drop from milliamps to microamps, drastically extending battery life from days to months or even years. Raspberry Pi. While Raspberry Pi has low-power modes, its operating system makes true deep sleep, where power consumption is extremely low, more complex, and less effective than on a microcontroller. Raspberry Pi is generally not suitable for extreme low power, long-term battery operation unless carefully designed with external power management. Disabling unused peripherals. Many microcontrollers and single-board computers have built-in peripherals like Wi-Fi, Bluetooth, or USB ports. If you're not using them, disable them in your code or hardware configuration if possible. Even idle components draw some power. Intermittent operation. If your application doesn't require constant data, only perform tasks or transmit data when absolutely necessary. For example, a temperature sensor might only need to send data once an hour, not every second. Optimizing code. Efficient code that completes its tasks quickly means the microcontroller spends less time awake and can return to sleep sooner. 9.5 Power regulation. Ensuring stable voltage. Components often require a very stable voltage to operate correctly. Batteries, especially when fully charged or nearing depletion, can have varying voltage outputs. Linear regulators. These components take a higher, potentially unstable input voltage and convert it to a precise, stable output voltage, e.g., converting 9V from a battery to 5V for your Arduino. Pros. Simple, inexpensive, generate very clean, stable output voltage. Cons. Inefficient. They essentially burn off the excess voltage as heat, meaning they waste energy. Not ideal for battery-powered applications where efficiency is key. Switching regulators, buck converters. These are much more complex, but also much more efficient. They rapidly switch on and off, converting the input voltage to the desired output voltage with minimal energy loss. Pros: highly efficient, often 85 to 95%, generate less heat. Ideal for battery-powered projects. Cons: more complex, can introduce some electrical noise, slightly more expensive. Many Arduino boards include on-board linear regulators, allowing you to power them from a 7 to 12V DC input, like a 9V battery or a wall adapter, directly. Raspberry Pi usually requires a stable 5V input from a good quality power supply. Conclusion and chapter summary. Effective power management is a cornerstone of robust IoT design, allowing your devices to operate reliably and persistently over their intended lifespan. We've dissected the core concepts of voltage, current, and power consumption, crucial for estimating and optimizing energy use. We then explored the spectrum of common power sources, from convenient USB adapters and versatile batteries, including caution regarding LiPo safety, to sustainable solar solutions, guiding you on how to select the right one for your project. Most importantly, this chapter outlined key strategies for energy efficiency, emphasizing the transformative impact of sleep modes for microcontrollers, strategic component selection, and intermittent operation. Finally, we touched upon the role of power regulators in ensuring stable voltage, distinguishing between efficient switching regulators and simpler linear ones. With a device that can sense, act, speak, connect to the cloud, and now manage its own power, you're well on your way to building truly autonomous IoT solutions. However, in our increasingly connected world, this connectivity introduces new challenges, particularly around the security and privacy of your data and devices. Our next chapter will delve into securing your connected world, exploring how to protect your IoT projects from vulnerabilities and ensure responsible data handling. Chapter 10: Securing your connected world, IoT security and privacy. You have meticulously crafted your IoT device. It senses, acts, communicates, connects to the cloud, and manages its power efficiently. It's a remarkable piece of engineering. But a connected device without adequate security is an open door, not just to your personal data or home network, but potentially to wider vulnerabilities across the internet. In an age where everything from baby monitors to industrial control systems are connected, understanding and implementing security and privacy measures is not just good practice. It's absolutely critical. 10.1 Why IoT security is critical. Protecting data, devices, and peace of mind. The stakes for IoT security are often higher than for traditional IT. A hacked computer might mean compromised data. A hacked IoT device could mean compromised data. Sensor data could expose sensitive personal details, e.g., your routines in a smart home, health data from a wearable. Physical harm. Malicious actors could manipulate actuators to cause physical damage, e.g., altering temperature in an industrial process, unlocking doors, tampering with vehicles. Privacy invasion. Devices often collect highly personal data, audio from smart speakers, video from cameras, that, if mishandled, could expose intimate details of your life. Network compromise. An insecure IoT device can serve as an entry point for attackers to gain access to your wider home or corporate network. Botnets and distributed denial of service, DDoS, attacks. Insecure devices can be hijacked and used as part of massive botnets to launch attacks on other internet services, slowing down or disrupting entire areas of the web. Anecdote: the Mirai botnet. In 2016, the internet was hit by unprecedented distributed denial of service, DDoS, attacks. These attacks were primarily launched by a massive botnet known as Mirai. What made Mirai unique and terrifying was that it didn't primarily consist of hacked computers, but rather tens of thousands of common, interconnected IoT devices. IP cameras, digital video recorders, and home routers. Many of these devices had easily guessable default usernames and passwords that their owners never changed. Mirai scanned the internet for these vulnerable devices, infected them, and then used their collective power to flood target websites with traffic, effectively shutting them down. This event starkly highlighted the real-world danger of insecure IoT devices, transforming mundane gadgets into weapons for cyber warfare. 10.2 Common attack vectors in IoT. Understanding where vulnerabilities typically arise helps in designing defenses. Weak credentials, unauthorized access, default usernames and passwords, like admin123456, are the easiest way for attackers to gain control. Lack of strong authentication mechanisms makes it trivial to compromise devices. Insecure networks and communication. Data transferred without encryption, plain text, can be intercepted and read. Unsecured Wi-Fi networks make devices vulnerable. Vulnerable software firmware. Bugs or unpatched vulnerabilities in the device's operating system or application code can be exploited by attackers. Many IoT devices never receive security updates. Lack of physical security. If an attacker can physically access the device, they might be able to extract sensitive information, like encryption keys, or load malicious firmware. Insecure cloud interfaces. Weak passwords, unpatched cloud services, or poorly configured APIs can expose the data collected from your devices. Privacy compromise. Devices collecting sensitive data without proper consent or clear privacy policies. Data being transmitted to third parties without user knowledge. 10.3 Security best practices for your devices. While professional IoT security is a complex field, for hobbyists and makers, implementing core best practices can significantly enhance your project's security posture. Strong, unique passwords, no defaults. Rule number 1. Never ship or deploy a device, even a prototype, with a default username and password. Ensure any Wi-Fi passwords, cloud API keys, or device login credentials are long, complex, and unique. Change them regularly. If your device connects to your home Wi-Fi, ensure your Wi-Fi network itself uses WPA2 or WPA3 encryption with a strong password. Encrypt communication, TLS SSL conceptually. Just as you use HTTPS// for secure web browsing, your IoT devices should encrypt their data when communicating over the internet. This is typically done using TLS, Transport Layer Security, often referred to as SSL. How it works conceptually: TLS creates a secure, encrypted tunnel between your device and the cloud server. Even if someone intercepts the data packets, they won't be able to read the contents because they are scrambled, encrypted. Most reputable cloud IoT platforms, like Adafruit.io and MQTT brokers, support TLS. Ensure your device's code is configured to use secure connections. Regular software firmware updates. Just like your phone or computer, IoT devices benefit from regular updates that fix bugs, patch known vulnerabilities, and introduce new security features. If your device uses an operating system, like Raspberry Pi OS, keep it updated using built-in methods, e.g., sudo apt update and sudo apt upgrade. For microcontrollers, try to use libraries and frameworks that are actively maintained and updated. If possible, design your device so that its firmware can be updated remotely or easily. Device authentication. Beyond just passwords, devices should ideally prove their identity to the cloud platform using secure keys or certificates. This ensures that only authorized devices can connect and send data. Many cloud IoT platforms provide unique device certificates for each registered device, which your device uses to establish a trusted connection. Least privilege principle. Give your device only the permissions it absolutely needs to function. If it only needs to send temperature data, don't give it permission to control other devices. This limits the damage an attacker could do if they compromise the device. Physical security. Consider who might have physical access to your device. If it's in a public place or accessible to intruders, simple measures like secure enclosures, tamper detection, e.g., a simple switch that alerts if the case is opened, and protecting exposed ports can deter basic attacks. Avoid storing sensitive information, like Wi-Fi passwords or API keys, directly in plain text on the device's storage if it's easily accessible. 10.4 Privacy considerations. Beyond explicit attackers, IoT devices raise significant questions about privacy. Who owns the data collected by your smart home devices? How is it used? Data minimization. Collect only the data that is absolutely necessary for your device to function. If you don't need real-time temperature data every second, don't collect it. Anonymization/pseudonymization. If possible, remove or obscure personally identifiable information from the data before it's stored or analyzed. Transparency and consent. If you deploy a device for others to use, be transparent about what data is collected, why it's collected, and how it's used. Obtain informed consent where appropriate. Data ownership. Be clear about who owns the data collected by your device. As a creator, are you retaining ownership, or is it truly the user's data? Ethical implications. Consider the broader impact of your device. Could it be misused for surveillance or discriminatory practices? Designing with ethics in mind from the start is crucial for the responsible development of IoT 10.5 ethical implications. Data ownership and surveillance. The rise of IoT intertwines technology with deep ethical questions. As devices become more integrated into our lives, collecting intimate details, conversations from smart speakers, health metrics from wearables, location data from cars, the ethical responsibilities of creators and users grow. Data ownership versus service providers. Often, the terms of service for smart devices grant significant rights to the device manufacturer or service provider over the data generated by the device. Does the user truly own their data, or are they simply granting permission for its use? Continuous surveillance. Smart cameras and microphones, intended for security or convenience, can inadvertently or intentionally become tools for continuous surveillance. How do we balance security needs with privacy rights? Bias in algorithms. If AI/ML models are used to analyze IoT data and make decisions, biases present in the training data can lead to unfair or discriminatory outcomes. Potential for misuse. A connected device might be designed for a benevolent purpose, e.g., monitoring elderly relatives, but its capabilities could be misused in unintended ways, e.g., monitoring without consent or even blackmail. As creators, we have a responsibility to design devices not just for functionality, but also with security, privacy, and these broader ethical considerations at the forefront. Building a reputation for trustworthy and secure IoT starts with fundamental principles. Conclusion and chapter summary. IoT security and privacy are not optional extras. They are fundamental requirements for responsible device design. We've explored the critical reasons why strong security is paramount, ranging from data protection to preventing devices from being hijacked into botnets, as painfully demonstrated by the Mirai attack. We then identified common vulnerabilities, from weak passwords to insecure communication, and outlined essential best practices. Using strong, unique credentials, encrypting all communication via TLS SSL, religiously applying software updates, implementing proper device authentication, and adhering to the principle of least privilege. Finally, we delved into crucial privacy considerations, advocating for data minimization, anonymization, and transparency, and touched upon the broader ethical responsibilities that come with creating devices that collect personal data. These principles form the bedrock of building secure and privacy-respecting IoT devices. Moving from theoretical knowledge to practical application is key. In our next chapter, we will shift our focus to real-world IoT, exploring tangible case studies and practical applications across various industries, showcasing how the principles you've learned are put into action. Chapter 11, Real-World IoT, Case Studies and Practical Applications. We've covered a lot of ground, delving into the underlying technologies, practical design considerations, and crucial security aspects of building IoT devices. Now, it's time to see how all these pieces fit together in actual applications. This chapter will showcase various real-world IoT case studies across different sectors, demonstrating the transformative power of connected devices and highlighting both their successes and the continuing challenges designers face. 11.1 Smart Home Automation. Beyond basic control. The smart home is perhaps the most visible and accessible application of IoT for many individuals. Advanced climate control. Beyond just learning your preferences, as discussed with Nest in Chapter 1. Smart thermostats can integrate with local weather forecasts to optimize heating-cooling and even participate in grid programs to reduce energy consumption during peak hours, earning credits for homeowners. Intelligent lighting systems. These go beyond simple on-off control. They can adjust brightness and color temperature based on the time of day, occupancy sensors, Chapter 3, and even integrate with entertainment systems, creating immersive lighting experiences for movies. Security and monitoring. Systems integrate cameras, door-window sensors, motion detectors, and smart locks to provide comprehensive home security. Alerts are sent to smartphones, and authorities can be automatically contacted. Facial recognition sensors, more complex for hobbyists, but conceptually relevant, are even emerging to identify family members versus strangers. Elderly care monitoring. Simple, non-intrusive sensors, motion, door open-close, bed occupancy, can monitor the routines of elderly residents. Unusual patterns, e.g., no movement for an extended period, door open at odd hours, trigger alerts to family members or caregivers, providing peace of mind and enabling independent living for longer. Real-world challenge, interoperability. A major pain point in smart homes is often the fragmentation of ecosystems. Different brands might use different communication protocols, Wi-Fi, Zigbee, Z-Wave, Bluetooth, and proprietary cloud services, making it difficult for devices from different manufacturers to seamlessly communicate with each other. This often requires users to purchase a central hub or rely on platforms that act as translators. 11.2 Environmental monitoring. Protecting our planet. IoT plays a vital role in understanding and protecting our environment. Air quality monitoring. Networks of small, connected sensors, like those using discussed gases sensors in Chapter 3, can continuously monitor pollutants, e.g., carbon monoxide, particulate matter, in urban areas. Data is sent to the cloud, allowing city officials to identify pollution hotspots, issue alerts, and make data-driven decisions to improve air quality. Water quality and level monitoring. Sensors deployed in rivers, lakes, or reservoirs can monitor water levels, temperature, pH, and chemical composition. This data is critical for flood prediction, drought management, and detecting pollution events to protect ecosystems and human health. Wildfire detection. Remote sensors in forests can detect early signs of a wildfire, such as sudden spikes in temperature or smoke particles. These LoRa-enabled devices, Chapter 6, can send alerts from even the most inaccessible locations, enabling faster response times and potentially saving vast areas of natural habitat. 11.3 Agricultural IoT, Agri-Tech. Precision farming for a growing world. IoT is revolutionizing agriculture, making it more efficient, sustainable, and productive. Precision irrigation. Soil moisture sensors, Chapter 3, embedded in fields provide precise data on water needs. This allows automated irrigation systems, controlled by actuators like valves, Chapter 4, to deliver the right amount of water exactly where and when it's needed, reducing water waste and improving crop yields. Crop health monitoring. Drones equipped with multispectral cameras can monitor crop health, detecting early signs of disease or pest infestations. This data, combined with weather station data from IoT sensors, allows farmers to apply pesticides or fertilizers precisely, minimizing chemical use and environmental impact. Animal tracking and health. Wearable sensors on livestock can monitor their location, activity levels, and vital signs. This helps farmers track herd movements, detect early signs of illness, and manage breeding programs more efficiently. Real-world challenge. Connectivity in rural areas. Many farms are in remote areas with limited internet access. This heavily influences the choice of communication protocol, often favoring LoRaWAN or cellular technologies over Wi-Fi. Power solutions, Chapter 9, often need to rely on solar or long-lasting batteries. 11.4 Health and wearables. Personalizing healthcare. IoT devices are increasingly personal, moving beyond simple fitness trackers to become integral parts of healthcare. Continuous glucose monitoring, CGM. Devices with tiny sensors placed under the skin can continuously monitor blood glucose levels for diabetics, sending data to a smartphone app that provides real-time insights and alerts about dangerous highs or lows. This empowers patients to manage their condition more proactively. Remote patient monitoring. For elderly patients or those with chronic conditions, IoT devices, e.g., smart scales, blood pressure monitors, vital sign patches, can collect health data at home and transmit it to healthcare providers. This reduces hospital visits, allows for earlier intervention, and provides a continuous picture of a patient's health. Smart wearables. Beyond fitness trackers, research is exploring wearables for detection of early onset of conditions like Parkinson's disease through analyzing gait and tremors, or for fall detection in the elderly. Real-world challenge: data security and privacy, HIPAA GDPR. Healthcare data is extremely sensitive. IoT devices in this sector must adhere to stringent regulations like HIPAA in the US or GDPR in Europe, which dictate how personal health information is collected, stored, and transmitted. This requires robust encryption, access controls, and transparent data policies. Chapter 10. 11.5 Industrial IoT, IIoT. Optimizing operations and safety. The application of IoT in industrial settings, IIoT, is about increasing efficiency, reliability, and safety in manufacturing, logistics, and supply chains. Predictive maintenance. As discussed earlier, sensors on machinery monitor performance metrics, vibration, temperature, pressure, acoustics. AI algorithms analyze this data to predict equipment failure before it occurs, allowing for scheduled maintenance rather than reactive repairs, drastically reducing downtime and preventing catastrophic failures. Asset tracking. Wireless sensors attached to valuable assets, e.g., shipping containers, tools, vehicles, monitor their location, status, and environmental conditions, temperature, shock. This data optimizes logistics, prevents loss, and ensures product quality. Worker safety. Wearable sensors for industrial workers can monitor gas levels, detect falls, track location in hazardous environments, and even monitor vital signs for fatigue. Alerts can be sent to supervisors in real time, improving emergency response. Supply chain optimization. IoT sensors can provide real-time visibility into the entire supply chain, from raw materials to finished goods. Knowing the exact location and condition of goods, e.g., temperature of perishable goods, helps prevent spoilage, reduce waste, and optimize delivery routes. 11.6 Smart City Initiatives. Building smarter communities. IoT is a cornerstone of ambitious smart city projects aimed at improving public services and urban living. Smart lighting. Streetlights with sensors can adjust their brightness based on ambient light levels or pedestrian vehicle presence, saving energy. They can also report outages or be used as nodes for other city sensors, e.g., air quality. Smart traffic management. Sensors detect vehicle flow and congestion, feeding data to adaptive traffic light systems that adjust signal timings in real time to optimize traffic movement and reduce bottlenecks. This can also inform navigation apps for drivers. Smart waste management. Sensors in public waste bins notify collection services when they are full, optimizing collection routes and reducing the number of trips, leading to fuel savings and reduced emissions. Public safety. Connected surveillance cameras, gunshot detection systems, and environmental sensors contribute to real-time situational awareness for emergency services. Real-world challenges. Scalability, interoperability, and maintenance. Beyond individual technical hurdles, large-scale IoT deployments face systemic challenges. Scalability. Managing hundreds, thousands, or millions of devices securely and reliably is a massive undertaking. Cloud platforms, Chapter 7, are essential here. Interoperability. Getting devices from different manufacturers, using different protocols and platforms to talk to each other seamlessly. Industry standards are evolving, but it remains a complex issue. Maintenance and longevity. IoT devices need to be maintained, updated, Chapter 10, and replaced over time. Ensuring long-term support and sustainable lifecycle management for devices deployed across vast areas is a significant operational challenge. Conclusion and chapter summary. This chapter has offered a glimpse into the vast and impactful world of real-life IoT applications. From making our homes smarter and improving our health to driving efficiency in agriculture and industry, and even transforming entire cities, connected devices are solving tangible problems and creating unprecedented value. We've seen how the concepts of sensing, acting, communicating, going to the cloud, and prioritizing power and security come together in diverse and innovative ways. Moreover, we've touched upon the inherent challenges that come with deploying and managing IoT at scale, such as interoperability between different systems, cybersecurity threats, and the need for robust long-term maintenance. The future of IoT is not just about connecting more devices. It's about connecting them intelligently, securely, and sustainably. In our final chapter, we will explore the emerging trends that are shaping this future, from advanced computing at the edge to integrating artificial intelligence and new networking paradigms like 5G, preparing you for what lies ahead in the continually evolving landscape of connected intelligence. Chapter 12, The Future of Connected Intelligence, Emerging Trends in IoT. You've journeyed from understanding the fundamentals of IoT to building your first connected device, securing it, and exploring its vast real-world applications. But the Internet of Things is a rapidly evolving field. What's next? This final chapter offers a look into the emerging trends and technologies that are shaping the future of connected intelligence, providing a glimpse into the innovations that will further blur the lines between the digital and physical worlds. 12.1 Edge Computing. Smarter devices, faster decisions. Historically, most IoT data was sent to the cloud for processing and analysis. While powerful, this approach has limitations. Latency. The delay introduced by sending data to the cloud and waiting for a response can be too long for time-critical applications, e.g., autonomous vehicles, real-time industrial control. Bandwidth. Sending all raw data to the cloud can consume enormous amounts of network bandwidth and incur significant costs. Privacy security. Transmitting all data to the cloud can raise privacy concerns, especially for sensitive information. Edge computing addresses these challenges by bringing computation and data analysis closer to the source of the data, to the edge of the network, which means on the device itself or on a local gateway. How it works. Instead of sending raw video streams to the cloud for analysis, an edge device, like a powerful Raspberry Pi or an industrial gateway, might process the video locally, detect an anomaly, and only send a small alert message to the cloud. Benefits: reduced latency. Decisions are made almost instantly, critical for applications requiring immediate action. Lower bandwidth costs. Only processed, analyzed, or filtered data is sent to the cloud. Enhanced privacy security. Sensitive data can be processed and discarded locally, minimizing its exposure to the public internet. Offline capability. Devices can continue to function and make decisions even if the internet connection is temporarily lost. Impact. This trend pushes more intelligence and decision-making capabilities onto the devices themselves, making them more autonomous and responsive. 12.2 AI and machine learning at the edge. Intelligent devices. Building on edge computing, integrating artificial intelligence, AI, and machine learning, ML, directly into IoT devices or local gateways is a significant trend. How it works. Instead of requiring a constant cloud connection for complex analytics, pre-trained AI/ML models can be deployed onto edge devices. This allows a device to perform tasks like local anomaly detection. A sensor might learn the normal patterns of a machine's vibrations and instantly detect an unusual pattern indicating a potential failure, without consulting the cloud. Image recognition. A smart camera at the edge can identify specific objects, people, or events without sending high-resolution video to a cloud server. Predictive maintenance. Devices can analyze their own performance data to predict when they might need servicing. Benefits. Transforms devices from mere data collectors into intelligent, proactive decision-makers. Enables new applications in robotics, surveillance, and smart manufacturing. Example. A Raspberry Pi running a compact ML model to identify specific bird species from a microphone feed, only uploading clips of rare species, rather than continuously streaming audio. 12.35 G and IoT, the network of tomorrow. The rollout of 5G cellular networks is set to have a profound impact on IoT, offering capabilities far beyond previous generations. Faster speeds enables real-time streaming of high-definition video from multiple cameras, faster data transfer for complex devices. Ultra-low latency, crucial for mission-critical applications like autonomous vehicles, drone control, remote surgery, or industrial automation, where even milliseconds of delay matter. Massive Machine-Type Communications, MMTC, designed to support an unprecedented density of connected devices per square kilometer, allowing billions of IoT devices to coexist and communicate efficiently. Network slicing, operators can create virtual networks optimized for specific IoT use cases, ensuring dedicated bandwidth and performance for critical applications. Impact: 5G will enable entirely new categories of IoT applications that demand high speed, low latency, and connection density, pushing IoT into truly pervasive and mission-critical domains. 12.4 Blockchain for IoT, ensuring trust and transparency. Blockchain, the distributed ledger technology behind cryptocurrencies, is being explored for its potential to enhance security, trust, and transparency in IoT ecosystems. How it works: each transaction or data point is cryptographically linked in a chain of blocks, making it extremely difficult to tamper with. Data is managed by a decentralized network, not a single authority. Potential applications: secure data integrity, ensuring that sensor data hasn't been altered from its origin to its destination, critical for supply chain tracking, food safety, or regulatory compliance. Device identity and authentication, providing tamper-proof identities for devices to prevent counterfeiting or unauthorized access. Automated transactions, enabling devices to securely conduct microtransactions, e.g., a smart meter paying for electricity, an autonomous vehicle paying for charging. Decentralized data sharing, allowing different stakeholders to share and access IoT data securely and transparently without relying on a central intermediary. Impact: can build greater trust in IoT data and foster new decentralized business models. While still in its early stages of practical application for IoT, its promise for areas requiring high integrity is significant. 12.5 Digital twins, bridging the physical and virtual. A digital twin is a virtual replica of a physical asset, process, or system. It's updated in real time with data from its physical counterpart through IoT sensors. How it works: sensors on a physical object, e.g., a wind turbine, a factory floor, a smart building, continuously stream data to its digital twin in the cloud. The digital twin then uses this data, combined with simulation models and analytics, to provide insights into the physical asset's performance, health, and potential issues. Benefits: real-time monitoring and diagnostics. Understand the current state of a physical asset. Predictive maintenance. Simulate different scenarios to predict failures, optimize performance, and plan maintenance more effectively. Optimized operations. Test changes virtually before implementing them in the physical world, minimizing risks and improving efficiency. Design and product development, used to design and optimize products before physical prototyping. Impact: provides unprecedented visibility and control over complex systems, leading to significant improvements in efficiency, uptime, and decision-making across industries like manufacturing, aerospace, and urban planning. 12.6 Sustainable IoT, building for a greener future. As billions of IoT devices come online, their environmental footprint becomes a growing concern. Sustainable IoT focuses on minimizing this impact. Energy efficiency, designing devices for ultra-low power consumption, as discussed in Chapter 9, leveraging renewable energy sources like solar. Circular economy for devices, extending the lifespan of devices through modular design, easy repair upgrades, ensuring secure and reliable updates, Chapter 10, and designing for easier recycling or reuse of components at the end of life. Reduced e-waste, minimizing the creation of electronic waste through durable design and responsible end-of-life management. IoT for sustainability, using IoT itself to monitor and optimize resource consumption, water, energy, manage waste, and improve environmental quality, e.g., intelligent irrigation, smart grid management. Impact ensures that the benefits of IoT are not outweighed by its environmental costs, contributing to a more sustainable future. 12.7 Human IoT Interaction. Natural and intuitive. The way we interact with IoT devices is continuously evolving, moving towards more natural and intuitive interfaces. Voice interfaces. Already common with smart assistants, voice will become even more integrated, allowing seamless control and interaction with a wider range of connected devices. Gesture control. Devices responding to hand movements or body language without physical touch. Augmented reality, AR. Overlaying digital information onto the real world, allowing data from IoT sensors to be visualized contextually, e.g., an AR overlay on a factory floor showing real-time temperature readings from machinery. Ambient intelligence. Systems that silently and seamlessly adapt to user needs and preferences without explicit commands, becoming truly invisible technology. Impact makes IoT devices more accessible, user-friendly, and integrates them more smoothly into our daily lives. Concluding thoughts, the evolving role of the IoT designer. The future of IoT is dynamic, exciting, and full of possibilities. The advancements in edge computing, AI, 5G, blockchain, and digital twins are pushing the boundaries of what connected devices can achieve. These trends highlight a shift. While understanding hardware, Arduino, Raspberry Pi, and software is still crucial, the role of an IoT designer is expanding. It now increasingly involves system-level thinking, designing complex, interconnected ecosystems, not just individual devices. Data science, understanding how to collect, analyze, and derive insights from vast datasets. Security and ethics, prioritizing the design of secure, private, and ethically responsible solutions. Sustainability, consciously creating devices with a minimal environmental footprint. You've built a strong foundation in this book. With this knowledge, you are prepared not just to participate in the Internet of Things revolution, but to actively shape its future. Embrace continuous learning, keep experimenting, and always consider the broader impact of your creations. The power to build a more connected, intelligent, and responsive world is now within your grasp.